Hello, hello, everybody. I hope you're doing well. It's good to see you all. Thank you for coming. Thank you for being here. Nick is just running a bit late, so no stress. We will be waiting for him. I hope you are all doing handy dandy. Yeah. So let's see who's in the chats. We have PJ Cruikshank. Good to see you. Lasky, thank you for coming. Better Than Gold, great to have you here. Moxie, Eleanor Strand, Sea Lightning, Dr. Bass Ackwards, Dot, Professor Harvester, Gematria Wombat. Um, yeah, it's good to see you guys. And Gary White Benga. Thank you all for coming, guys. Gary White Benga says, I was just listening to Beyond the Imaginary Curve. And Dell thinks that Earth is accelerating upwards. Yes, he does. He does think the Earth is accelerating upwards. He's got the same belief as the Flat Earth Society that it's a disk floating up in space. If he wants to believe that, that's his prerogative, I guess. Hey, Slip Radar, thank you for coming. Glad you could make it. Plain the truth. Hey, good to see you. Yeah, Nick is a Glober. He's got a PhD. I think he actually teaches students. So it's going to be great to see what he wants to chat about. We haven't really discussed a topic for discussion, but I know with him it's going to be epic because he is really a very nice all-around guy. Very, very how can I put it? He's not like FTFE, let's put it that way. He doesn't overtalk you and say stupid stuff. He's actually, we can have an intellectual discussion together. Oh, I missed some condensed milk. That's usually what I get for my birthday is a tin of condensed milk, and I decided to finish it now. So yeah, guys, by the way, I am going to be ordering my new mic and audio processor soon. Thank you very, very much for all the help, guys. Thank you. Big, huge shout out to Tony Wickham and Paul out there. Paul, you guys really, really did support me big time for helping me get this mic and processing unit. So that's going to be great. As soon as my money shows in PayPal, I'll be ordering my mic and processor. Then this audio issue is going to be a thing of the past, guys. Yeah, we settled on the Shure SM58 and I can't remember what the name of that audio processing is, but it's a single channel audio processor, which is really great and seems to work well with that. For the budget I've got, it's going to be a great setup, and I'm really looking forward to it. Hey, Detective, it's good to see you, mate. Thank you for coming. Yeah, I agree, Gary, that is crazy, but what can we do? His argument is simply water. When you place water in a bottle, if you accelerate, the water displaces away from the acceleration. The gas moves towards the accelerated vector. And that's his argument for why the Earth is accelerating upwards, because all the waters we have are down on ground level, which is a logical argument if he puts it in that context. But I think it's more logical to understand that we don't move at all and the water's just denser than the air around it. Therefore, it can't be supported by the air to lift it up. Oh, we got Nik Volt in. Hey, Nick. Good to see you.
Hey, good morning. My camera's not working, so.
Oh, no stress. We do know how you look. Don't worry.
Okay. Didn't want to think. I didn't want anybody to think I was hiding, but I don't know why it's not connecting. So.
Sometimes we have issues, and I'm definitely one to have shown issues these last few days.
It happens. It happens.
Yeah. Oh, but it's good to have you. Yeah. I almost thought you're not going to make it.
No, I was running home. Just lazy Saturday morning. So.
No, but you're doing well though.
Thank you. Thank you for asking. Yeah, I'm doing fine. Beautiful day here in Southern California.
Oh, that's great. Yeah. So, what topic did you actually want to discuss?
Well, what I'm curious about is, the way I approach science is and you probably already know this, you shouldn't go with a premise and then try to find evidence to fit that premise. And what I'm more curious at is, if we assume that the flat Earth model is real, how do other phenomena fit within that model, if that makes sense?
Like you're saying, established science that's already shown to be true. How does it fit in the flat Earth model?
Yeah, because science should always lead you to the conclusion, and I'm just curious about the flat Earth model, that there are things which I do not understand about it, which are explained by the more accepted model of the shape of the Earth versus the flat Earth. And I've heard a lot of, everybody has sort of their own weird theory about it. And like all good science, there's not one accepted theory. The one which has been fascinating me for the last few weeks is gravity.
Oh yeah.
I do not, and this is a legitimate question. I do not understand how, because many people who subscribe to the flat Earth model also say that there's no gravity. Yeah. Which to me is kind of confusing. I don't see why the two should necessarily be opposed to each other. I mean, could we not have a plane in space which has mass, which also has gravity? Like, why also deny gravity? That's what I don't understand. And I've tried to ask this question a few times. I went on your server. Everybody seems really obsessed with just shouting everybody down before even knowing what anybody's real theory is. And honestly, good science is, no, we don't make the claim. We follow the evidence, which eventually leads us to an undeniable claim. But the great thing about science is it has to fit within the model. I mean, if you can show 10 examples of why it is one way, but you show one example which doesn't fit and cannot be explained by us, then you've got a problem. And that's sort of what I was curious about. I mean, I've heard all of the arguments back and forth about line of sight, about this, about that. That's fine. But what about gravity? Why not gravity?
Because gravity is the glue for the globe. It's the thing that coalesces everything into a sphere. Because everything, you say, attracts to the center of mass.
Yes.
Yeah, you see, that's the problem. Gravity has never been scientifically validated. And the fact that gravity keeps on having to change because they find loopholes in it, that makes it a problem. How it would work now, if you want gravity, which isn't flat Earth, it sounds to me like you're trying to say, okay, because you don't believe in gravity, why don't you have it on flat Earth? It's simple, because you require your gravity on your model, for instance, to hold the gas pressure to stop equalizing to go into space, correct?
Well, no, not necessarily. I mean, we're getting into the minutia about that. Let's just first, at least maybe I can explain what us physicists call gravity, because I've heard a lot of interesting things about it, like you only show effects of gravity, you only show not the cause of gravity. Is gravity a force? Is it not a force? Is it a fictitious force? There's a lot of stuff going on here. And then, for example, it goes into this further discussion about, like you mentioned, gas. And I saw this in the chat on the channel, and a lot of talk about gas and this and that. But now we're talking about some, a little bit of chemistry, a little bit of this. But if we start with the premise, which is this, we say that anything in the universe that has mass has a gravitational field, which would include a gas and all of this. That's what I don't understand. Why deny that? Because one could actually show a flat Earth without denying gravity. I think the reason why a lot of us go bonkers when talking about flat earthers is it's not a true scientific theory, because it does not answer these questions. For example, yes, if everything gravitates to the center of mass, you would start getting spherical shapes, just like, water in 0G sort of coalesces amongst itself because of gravity. But then but then flat earthers also say, for example, asked, does Earth have an electromagnetic field? And they say, yes, it does. Well, you can't get an electromagnetic field without uh, without without something generating that field. And of course, we say that is,
Like the
our
dynamo effect.
dynamo.
Yeah,
And so
yeah.
that's where I wanted to start with. Like, why deny gravity?
But like I said, we don't. Gravity is actually just, how can I put it? It's constitutional just for the globe model. It's created specifically for the globe model. So it's not that we're denying gravity; it just doesn't exist to deny. The problem with gravity, it comes that you guys try and push the gravity theory. I'm just saying colloquial theory because it's not scientific, onto flat Earth because you already have the preconception that gravity has to exist to hold you down. You see, the foundation of how you guys are thinking is if I don't have something holding me down, I will fly into space, correct?
Not necessarily, but I think I know what you're trying to say. Yeah.
Because you guys already have that pre-notion thinking that the Earth is spinning around in space. So the centrifugal forces are too great. If you don't have something pulling you back to have an equal and opposite reaction, hence G, then you would fly off into space. So that's why you guys already have the fundamental understanding that, listen here, if I don't have gravity, then I will be flying away. Now that's the difference with us. We take that totally away and say, hang on, we don't need to worry about things holding us down because nothing has to counteract for flying away into space.
True, but just just like the flat Earth, I mean, a lot of science is based on observation. A lot of it is based on observation. Our eyes tend to be what our brains believe the most because, if I can see it, I believe it. Of course, that's not always the case. I mean, our eyes do deceive us, but, we start with that. For example, people say the Earth is flat because it looks flat. You go outside, you go to the ocean, it looks flat, right? I mean, that's just the way it is. And we tend to believe it. And as far as gravity, I mean, if I get on the roof of my house and I jump off, I am going to fall. And since birth, once we're able to sort of understand the world around us, we understand that you don't climb up on high ledges because stuff will fall. Everything goes. So there's something which is causing this to happen.
Yeah,
and that's where the science comes in.
Why?
Why is this happening?
That's the difference. You guys believe and you call it gravity, where we go and we say it's relative density disequilibrium, where it's simply that you are denser than the medium around you. So the air cannot support you, and thus you're denser. You're going down to your relative equilibrium point. Because now, you have the greater displacement of pressure.
What does that mean, greater displacement of pressure?
Let's take, for instance, Archimedes' principle. It's just displacement.
Okay. Yeah.
Yeah. So if a boat doesn't displace enough, it's going to sink. It's the same with you. If you are an object and you can't displace your density enough, you're just going to go down because the air can't support you.
Not exactly. I mean, density, if you want to talk about Archimedes' principle, it's more of a matter of, I mean, we're going to assume, standard physics here. And again, one of the other observations we sort of just make in the universe in our everyday thing is that no two objects can occupy the same point at the same place in space. For example, right now I'm sitting in my chair. I am occupying that space. I displaced the air, which was originally on top of my chair before I sat my behind on it. It got displaced. And what Archimedes says is, you in a tub of water, if you put something in there, let's say, Archimedes' body, the water has to, quote, get out of the way for his body to sit there because the water and the body cannot exist at the same time.
Yeah, it's causing an equal and opposite kind of reaction. That's why if you're sticking a cork in the water, it's floating because it's just displacing its own weight.
Yeah, but I mean, you could throw a stone in water and it would sink, but it's still displacing the water.
Yeah, the water around it. But if it's displaced enough, it would float.
Well, no,
That's why the whole of the ship is created to displace its weight.
well, I think you're maybe looking too much into it. I mean, we're just talking about displacement. Is that two pieces of matter cannot occupy the same space-time coordinate? Like, for example, you and I could not exist in the exact same space at the exact same time. One of us would have to, quote, get out of the way. And all that a liquid is, all that a gas is just a state of matter. It's really not that different. Obviously, gas is, the distance between each molecules is greater, so we can more easily move through it. But that's really all Archimedes was saying. It still doesn't change the fact that objects fall, and they fall at the same rate, and there has to be a reason for this.
Yeah, as I say, and it's all medium dependent. That's why the 9.8 meters per second is based in a vacuum, correct?
No. Well, it's 9.81 meters per second, what we use as what we call G sub E, or gravitational acceleration. Maybe we should start with that, because I did notice there's some confusion with some of these terms. And I did watch your debate yesterday, and I don't want to get bogged down on terms. We're not going to be arguing semantics here, because I understood what both of you people were trying to say. But there are clear distinctions here. For example, gravity is not the same thing as gravitational acceleration. And mass is not the same thing as volume, which is not the same thing as weight. These are all different things. Granted, they are related, but they are fundamentally different things.
That's what I like about you, because a lot of the people, especially like with Craig, if I have to debate with them, they would say they're the same thing without understanding. They can't really give a definition of gravity. Would you be able to give us maybe a definition of mass for us?
Well, this is the way I explain it to my students, just, sort of a beginning way to. Mass just represents a way to quantify an amount of matter. That's it. That's it.
It's like, yeah, but you understand mass is like, it's simply inertia, because you're resisting the urge to move to distance inertia.
Well,
so it's the same as inertia.
Not necessarily. I know where you're going with that, and that's, we can get into that why, and maybe I can clear this up for even people who do accept gravity, like why we say gravity is not a force. But I mean, mass is just a way to quantify the amount of matter.
I agree.
For example, I have my Dr. Pepper in front of me, and I can measure its mass. That's it.
Yeah, that's why I love density so much, because you have, how I like to say it in very simple terms, it's simply the substance crammed into a volume. That's it.
Yeah. And even sort of going on that point, like, for example, I have ice in my cup, right? So if I were to melt this ice, it would have the same amount of mass as it would when it's frozen. That's absolutely true. Like, I don't just create mass. I don't just sort of and give it away. However, its density changes
because of the spacing. Yeah.
I mean, in fact, one of the new interesting properties about ice is that when it freezes, we tend to think of solids being more dense than liquids, but it's actually otherwise there would be no life on Earth. Imagine exactly. Frozen ponds sterilized everything below them. It wouldn't make any sense.
Yeah. But you see, that's why I enjoy having you on. We can actually have an actual conversation. We don't have to, how can I say, have it. You saw last night with Craig. With the anti-flat earthers, it's difficult to have an actual grown-up conversation with him, I can say.
Yeah. Craig was correct, though. You can have a map without a grid.
Yeah, but I was referring it to navigations. That's what I was referring it to.
Yeah, well, navigation is a really interesting. I mean, we credit the British who really made, and not to get too far off topic, but I mean, the way we navigated this, the seven seas is pretty fascinating. I mean, it's almost vital to our development as a civilization. I mean, the ability to cross these great oceans is, what give us all the things which we have now. But I never really understood why deny gravity. I mean, just because
Well,
I mean, would not a flat Earth have mass?
everything has mass. If you have substance, if you physical, you got mass, obviously, because it's something. It's physical. But the issue comes in when you have a belief that that something is attracted to another thing.
Well, we can show that it is. I mean, there are countless. I mean, like I said before. I mean, we've shown this. It's not even a very complicated experiment. Like I said, in one of my undergraduate general physics courses, we're doing this. We're doing the experiment to kind of show gravitational acceleration. And you are correct in that experiment. We do model or we do treat gravity as a force. Doesn't mean it is a force. It's just ultimately. I mean, let me put it another way. Why do we do experiments? Why do we do all of these things? And here, actually, let me make this simple. And this is why I think what the other person was trying to say, the burden of proof is upon those who believe the flat Earth to show that the Earth is flat versus the other way around. Because the ultimate goal of studying all of these things is not necessarily so, hey, look, we know how to do all this stuff, but rather, or we know why this stuff works, but it's rather to make predictions. That is the whole point. We need to be able to make repeatable predictions. And once we're able to do that, then we can start building these nice, beautiful things like aircraft, cars, stuff like that. And the flat Earth model, and this is why I wanted to talk to you, because I've asked a lot of flat earthers this, some in the chat. Generally, they don't answer the question, or they don't really understand why the world is flat. They just copy and paste some link to some other freak on the internet who's, I'm not saying you're a freak, but you know what I meant. Like some other person going, oh, this is why the world is flat. And then I try to go question them. And then they just link to some flat Earth wiki and like, okay, no. We need to be able, if the world was flat, then we should be able to go out and test it. I think that's really what science is trying to say is we need to come up with an experiment which we can test whether the flat Earth model prevails or a spherical Earth prevails, or how do we even know it's not a pyramid, right? I mean, why couldn't it be a pyramid? Just because it's not flat doesn't necessarily mean it has to be a sphere. We have to go where the evidence leads us to.
Would you be able to maybe define what you would say science is?
Well, science, there are people who are much more qualified than I am to do that. I think all of us have a basic understanding of sort of what we call the scientific method, where we collect data, we look for patterns in that data, we try to find ways, because if there's a pattern, that means it's predictable. We try to draw up then the equations of that repeatable pattern. I mean, essentially, mathematics is the language of the universe. And that leads us to a conclusion, which will ultimately lead us to say, okay, this is why it happens. For example, I live here in California. We have a lot of earthquakes, right? And we had this, the prevailing theory of what causes earthquakes is the theory of plate tectonics. Do we actually see giant continents moving around planet Earth? Well, no, but we see evidence of it. And all of that evidence fits within this model. We could show a piece of evidence which doesn't fit into that model. Then, we throw the theory out. The problem with the denying the globe is we don't have any evidence which negates that model.
Okay, but let's put it this way. Would you say gravity has been scientifically validated?
Yeah, gravity is a thing.
Okay, so let's take
and let's not get confused. I'm going to call it a force. There are 4 fundamental forces in the universe, and 2 of them you and we already deal with every day. One is the electromagnetic force, and one is gravity. The 2 other forces are kind of interesting. They have very creative names. They're called the strong force and the weak force.
And the weak force, yeah.
Yeah, but those are more when we get into at the scale of an atom. But so we've shown.
Like I'm trying to ask though. Like you say, gravity is scientifically validated. So let's start at the beginning with Newton when he proposed gravity. Would you be able to give me the hypothesis and experiment that he postulated gravity to?
Well, so Newton at first didn't come up with this idea of gravity, and that sort of leads to, we'll get to I think what you're alluding to is the what do you call it, the Cavendish experiment. I never can pronounce it right, but, the two masses, this and that. But what Newton postulated was something called gravitational acceleration. Who knows if the story is true, but it's a great anecdote. Apples fall out of trees. Okay, so apples fall out of trees, and the longer you fall, your velocity increases. So he says, okay, it's an acceleration vector, and that's what we call gravitational acceleration.
Yeah. And that's just simple physics. You don't start at a top speed. You start at zero. So obviously you're going to accelerate.
Yeah.
But like I'm asking specifically, because he postulated gravity, what was his hypothesis and experiment to go and say to the world, listen here, I think this is what's happening and this is my reason?
Well, because so as the story goes, I mean, in order to do what we call these equations of motion, which take into account some sort of phenomena that's causing objects to accelerate towards the ground. I pick something up, I let it go, it drops. The higher I drop it, the higher its velocity is when it hits the ground. It's just acceleration. He called it gravitational acceleration. Didn't say what was causing it.
Depends when it hits terminal velocity, though.
Well, yeah. I mean, you go a further distance, but when you're within a short amount of range, we can sort of negate those extra variables. That's why we say let's assume ideal conditions. It's not that we're throwing away terminal velocity or this. You're just saying that at this distance, the effects of air resistance would be negligible. So we can just sort of like throw it out of the equation. And then he had to come up with, I mean, really, if you want to start with Newton, remember, Newton was looking for a way to quantify the universe. And this is what I tell my students. Us scientists, we sort of make a couple of assumptions. There is stuff which I hear because I'm just sort of observing the chat. I see the word prove get thrown around a lot. We got to prove this. There are a couple of things which we can never prove. I can't prove to you that the universe exists. I can't do that. I have to assume that it exists. And I also can't prove to you that you and I are actually having this conversation. These are assumptions. And so you say the universe exists. We exist within inside of it. And then we say we assume that it's knowable. And that term knowable means we can quantify it. Yeah. For example, you and I can look at the color blue. Both of us could look at this color and we could both agree that it's blue. But I don't know what blue looks like to you. You don't know what blue looks like to me.
It's funny that you brought this up. I actually did a thesis on this color misconceptions when I was in high school, where that was one of my theories I had to put up. It was, how do I know my orange is your orange?
Yeah, exactly. No, that's actually a pretty sophisticated thing to think about, which is why we came up with mathematics. Because even though we can't prove to each other which one it looks like, both of us can agree that we can quantify its wavelength and say, blue is approximately, I forget what it is off the top of my head.
To you could see it in a different wavelength than me, but because you already know that's what you were taught as that wavelength, you're going to see it as that color, and I'm looking at the same one. We know automatically it's the same, but who says mine is exactly the same as yours?
Yeah, and that's why we need mathematics to quantify it. And that's sort of what Newton was saying. It's like, look, anytime you have objects which are in motion, when something is moving, it means that it's in a state of change. For example, the car travels from point A to point B. It's moving. It's in a state of flux. How do we make sort of predictions about that? How fast it's moving, how far it will be after a certain amount of time. If it's accelerating, how long it takes to accelerate, how long it takes to decelerate. These are all what we call rates of change, which is why Newton, along with, this mathematics was kind of developed independently at the same time between Leibniz and Newton, which is where we get calculus. This idea where we can find these rates of change. And so acceleration is a rate of change, going from 0 to 60 per some rate. How does my velocity change with respect to time?
Yeah, but
And that's all he was doing. He wasn't out looking for gravity. He was just out, how do I quantify motions which allow us to make predictions?
yeah, because I mean, he didn't really want to be associated with anyone. And I think it was C.V. Boyles that came afterwards and ascribed it to Newton. Um, but the question I wanted to ask you, would you not understand that because things have terminal velocity, it actually goes against the notion that gravity is attracting mass to mass?
No. Terminal velocity is, you're talking about air resistance.
Yeah, but you
Or
can have terminal velocity in a vacuum as well, can you not?
no,
How do you
no.
know?
And in fact, that's what Newton's laws are. So, and one of the funny things about Newton's laws, see, Newton, we all think of him as, he's this great, brilliant person. Newton's laws didn't explain anything. In fact, that's what a law is. He just said, this is just a law. The question is why. In fact, this is a classic example of the idea of show me proof of gravity versus the effects of gravity. The laws only show you the effects. They don't tell you why.
And that's why I agree with you. That's why when I say you didn't even have to call it gravity because it's just simple physics. We can take that acceleration and we can call it unicorn if we want to, and it has the same effect. It's just not going to be called gravity. Because that's how physics works. We observe every day things accelerate downwards, just like he was trying to explain due to physics. The problem comes when you take that physics and you push a pseudoscientific belief that because things accelerate in mass to mass, therefore we have planets in space. Because that's pseudoscience, because that gives you a belief based on actual physics that's established.
No. You're making this huge leap from just we observe objects falling to why, because now you're getting into, well, we've got Kepler, you've got Tycho Brahe, again, also based on observation. I mean, we know that we have planets because we can see them. We can see them with our own two eyes. They exist, and they behave in a way that leads us to the conclusion, like, for example, whether the sun is in the middle of the solar system or whether Earth is in the middle of the solar system, our observations show us that it has to be this way and cannot be this other way. Because if it were the other way, let's say if Earth were in the center of the solar system, then the motion of the planets would not behave the way they do. And that's really all science is.
See, that's the problem. The fundamental is, again, based on having a belief of space, having a solar system, having a belief that those planets you see is the same on the ground we stand on. It's just correlative. It's not causative. And science is simply causative. You would agree that science is causative based.
I'm not sure I'm following you. Maybe
let's take, for instance, like I was asking you, the hypothesis. The hypothesis, you would understand, is simply to find a cause for an effect that you observe.
Yeah, I could say that. Okay.
Yeah,
I'll go with that.
So it's not correlative. You would have to actually go and manipulate what you think caused the effect. So you would manipulate the independent variable, so the dependent variable would show the effect.
Oh, okay. Well, actually, no. I mean, let's take gravitational acceleration. Let's keep this simple. Suppose let's say we don't know that objects accelerate towards the ground at 9.81 meters per second. Let's say we don't know that. How would we go about determining this number? Because all of these values came from experimentation. Newton didn't sit there just one day, or I didn't sit there one day and just say, yes, students, gravitational acceleration is 9.81. We have experiments which lead us to that. We experimentally find this out. And so how would we go about doing that?
Yeah. What experiments did Newton do there?
Well, instead of, let's say, acceleration going down, suppose I took maybe a skateboard, right? I know Newton did, but something with wheels. And I wanted to know if I push it with a certain amount of force, how much does it accelerate? So what I would do is when designing an experiment, one could argue that there's an infinite amount of variables that affect something's motion. So we try to eliminate those variables. And yeah, it goes back to sort of like what we learned in grade school. You got an independent variable, you got a dependent variable. In other words, if I change this variable where I get to choose what I input into the system to see what output it gives me, what output does this function give me, then I very simply just sort of plot those data points. If I enter in A, it gives me X. If I enter B, it gives me Y. Plot it and then look for a pattern. And then from that, I can come up with an actual equation, which will then be able to make predictions. For example, if I know if I travel a certain amount of time at 60 miles per hour, I will be this far away from my origin. And that's essentially all Newton did. Now, it did require this thing which is called calculus, where they teach us from day one, thou shalt not divide by zero. Unfortunately, the world gets a little bit more complicated when you deal with physics. It's like, well, we got some way to be able to do that. So then it comes up with this idea of derivative and this and that. And then a lot of us don't study calculus, but we study algebra, and all of that's sort of based on it. And that's all it is. I mean, there's nothing really nefarious about it. That's why I never understood that. Why?
But you understand
why would I mean? Let's put it another way. As an educator, as a researcher, what would be my advantage of talking about gravity when I know it's not real? What would I gain from that?
Yeah, if it's not real, what do you gain from it?
But what would I gain from it?
Because that's what I'm trying to make my point is. We can agree then together. Newton wasn't actually talking about gravity. It was just simply establishing physics. This is the way things work, and the acceleration, it was contributed to gravity.
Yeah, and that's where Newton's laws comes in. It says, obviously, Newton says that a force is equal to an object's mass multiplied by its rate of acceleration. An object in motion tends to stay in motion, right? And for every action, there's an opposite but equal reaction. And again, these are just laws. Newton never told us why. He had no idea why. He just said, this is what we observe in the universe. And then came up with the mathematics. And see, here's where it gets difficult. And I know some say that, okay, well, it's just a cop-out, but you got to know the mathematics to fully to understand why these things are true. Because the one force in the universe which doesn't lie is mathematics. There's just no getting around it. And flash forward to the year 2023, I can take an object, drop it for a certain amount of time without me even testing it. I can tell you what its final velocity is going to be because we have the equations. And even if we go out and do it, we can repeat it over and over and over and over again.
Okay.
Something which a flat Earth can't do.
You can see my cup I got in my hand.
Yep.
Okay. Mathematically, we can just plus this by another cup and it said I have 2, correct?
As what? I'm sorry?
I can just take, I've got this cup, I'm going to plus 1. So I take up a plus 1. Mathematically, it will say I have 2.
Okay, yeah.
But in reality, I only have 1 cup.
Well, okay. So mathematics is the way of the universe, but unfortunately, we define mathematics. I mean, we count from one language. Yeah, it's even not even a language. I'd say it's just a tool. It's like having a screwdriver.
So it can also lie based on reality. So you can make up an equation, which it works out perfect with the math, but that doesn't prove its reality, though.
Well, that's the thing. That's why we go out and do experimentation. We look for patterns, and then we find the functions which fit that. For example, let's say I wanted to know the position of an object that travels at a certain velocity for a certain amount of time, right? There's an equation for that. Mm-hmm. And that equation is just based on data. It's a linear equation. We know that there's a linear relationship between a constant velocity, how long it travels, and what its final position is going to be. Then let's say, what about if it's accelerating? Well, then what will its final position be? Then we just sort of modify the equation based on the data. And then we can make these sort of predictions. Now, that's, I think, where the flat Earth gets in trouble, is where can we make repeatable, predictable results? If in fact if in fact objects do not gravitate or do not accelerate towards the center of mass at a certain rate, at what rate do they accelerate at?
But remember what we've just been talking about. There's no established science that proves or evidence that mass accelerates to the center of mass.
Well, right.
We've established that Newton only tried to explain the physics behind why things accelerate.
Yes,
but the thing that came in afterwards was the belief. That's why I said pseudoscience, that mass attracts mass. But even based on today's scientific explanation based on Newton general relativity, it's
Uh-huh.
only an effect. So that only effect actually totally contradicts Newton's gravity in the first instance anyway, because based on general relativity, the Earth is accelerating upwards constantly. So you, based in your reference frame, are not is not you are always accelerating. The person falling is static. So it's not
Yeah.
the apple falling to the ground; it's you rising up to the apple, and therefore it's
Okay.
not
Yeah.
a
No, I know where you're going with that. You're just talking about inertial frames. All that's saying is just the equations can be reversible. That's all. That's all it's saying. And the thing with Newton is Newton wasn't trying to explain why. We haven't even got why. We haven't talked about what gravity is. He has no idea what gravity is. We don't know anything about it at the age of Newton. All we know is that objects on planet Earth accelerate towards the ground at a certain rate. And since everything on planet Earth is subject to this force, which is wanting to pull it down, what we call weight or mass times gravitational acceleration. We can then build buildings and this and that and all that, but it says nothing about what causes it. Newton had no idea.
But then I've got to stop you again. You're saying there's a force pulling it down.
Well, Newton thought it was. He called it what do you call a fictitious force, kind of like centrifugal force. It's not a real force; it's fictitious.
And you would require a physical force present to have a fictitious force present, correct?
Well, actually, more simply, we could say that what Newton says: in order for an object to accelerate, you must apply a force to it. That's what Newton says.
So to have a fictitious force, you require an actual force present first.
Well, no. To accelerate an object, you require a force.
Yeah, but a fictitious force accelerates, correct?
Well, gravity, maybe fictitious is the wrong term I'm using. So in Newton's time, Newton called gravity a force. Okay. So I know now we say it's not a force, but let's just stick with Newton. And basically Newton said, like, I've got a big rock in my yard. In order for this rock to start moving, I got to apply a force to it to get it to move. If an object which has no forces being applied on it will not accelerate. Hence, an object in motion tends to stay in motion. An object at rest tends to stay at rest. If the net forces on that object are zero, then it will just continue on due to inertia, or it will just sit there by itself. Now, the cause of gravity. Now we got to jump forward to the time of Einstein. That's hella complicated. Let's stick with Newton right now. Because then we got to have a whole discussion about even what special relativity is before we can even get into general relativity. And I'll even admit for myself, some of those equations get pretty hairy. I mean, they use a whole different, like Einstein. I don't even remember how to write those equations because they use a different type of text. It looks really fancy, but it's complicated. It's complicated.
Yeah, with all the tensors and stuff, it's quite hectic. But the thing is, like I'm saying now, Newton, everybody can then see that it's simply he just wanted to explain the physics. He wasn't simply making the claim that it was gravity pulling down. The gravity pulling down as a force came afterwards because they took his laws of motion and said, hang on, because F equals ma, you require a force, so it's going down, so therefore the mass must be pulling it down. Am I saying that correct?
Well, what we say is anything with mass generates a gravitational field. So yeah, it's because the Earth has mass, it generates a gravitational field, which causes objects to accelerate towards its center of mass at 9.81 meters per second. That rate of acceleration is dependent upon the magnitude of the mass. For example, if you're on Jupiter, the gravitational acceleration on Jupiter is larger, and then the sun is even larger. It's essentially your mass determines what that acceleration rate would be.
But you see, that's the problem again. You're just going to begging the question. I mean, how did the guys explain then? I mean, obviously this is where they came with buoyancy. When you, for instance, take a balloon and the balloon goes up and not down. The thought pattern should be, my hypothesis is things fall down due to gravity pulling it down, but now I see things going up. So hang on, my hypothesis was just shown invalidated because my hypothesis is simply mass attracts mass, and helium also has mass, but it went the opposite direction of what my hypothesis was validated previously. So it invalidated it. So what did they have to do? They had to do what they call the God of the gaps argument, and they had to recreate another facet of saying, I know what the problem is. It's now displacement, so it's forcing it upwards. And that's
why I see where you're going with this. I think you're confusing something, though. See, when a hot air balloon goes up in the air, it's still subject to gravitational acceleration. There is still something which is causing it.
Helium. I was speaking about a helium.
But we counteract that force. Remember, the whole idea is to counteract the force. For example, we've all seen aircraft fly, right? We'll all agree that aircraft is pretty dense. It's heavier than air. But we see aircraft go up in the air. It's because, because we generate lift. And if we can generate a vector which is greater than our weight vector, then, we go up in the air. And if the gravitational vector is greater than lift, well, then we come back down. I mean, it's not necessarily have anything to do with density. For example, a hot air balloon will create a upward buoyancy force, which is greater than your vector mass times gravitation.
That's what I'm saying. That's what I'm saying. The buoyancy argument came from them saying, we have a problem with our hypothesis, because our hypothesis is all mass is attracted towards mass. But hang on, Billy stands here, his helium balloon goes up. So that now invalidated their previous hypothesis. So they created a new one saying, yes, mass still attracts mass, but now we have the displacement of that mass which causes it to go up. You see what I'm saying? They just created God of the gaps argument. And that's why gravity keeps on, how can I say, inclining to a new type of gravity. And that's why Einstein came in. And now they're trying to push like Eric Philinder's entropic gravity. You've heard of entropic gravity before.
Yeah, but I don't think it applies here. I think you're overcomplicating it. Like, take your cup again. Take your cup, sitting on your desk right now, right?
Okay, that's on my hand, yeah.
You picked it up, right? So you must have. You didn't make it less dense than air.
I imparted energy into it, correct? It took energy. I transferred energy.
You put a mechanical force onto it, which overcame gravitational acceleration. That's it.
Didn't overcome anything.
Density is not.
That's my point. It didn't overcome anything. I simply picked it up.
It overcame gravity.
No, that's my point. I picked it up from its relative equilibrium. It's now sitting static.
Yeah, it's sitting down there. The table itself is providing a normal force, which keeps the cup up.
So the air is not able to support the cup. So the cup has a larger pressure. It's pushing down because it's heavier, because it's larger pressure. It can't displace enough of its weight for the gas to be able to support it. Okay.
I'm not following you. Sorry, I don't understand what you mean by gas.
We're in a medium. Gas is a medium.
Gas is a medium, just like solid, gas, plasma.
So you understand, if you have enough gas pressure, it can lift something. It can support a weight if it has enough, like the Magnus effect. Let's say you've seen the Magnus effect when they take the ball and they stick it on the edge of a leaf blower, and it's staying above, just spinning in the air.
What do you define a force as? Well, let's start with that. I think maybe there's some disconnect there, because the air has nothing to do with the fact that your arm is able to lift your cup up off the desk. Nothing. I mean, this would happen in a vacuum too. Exactly the same.
Well, let's put it this way. If you were in a very dense liquid, let's say you were in a pool of very dense starch, okay, but it was enough to hold you down in there, would it be more difficult to lift your arm up? You have more friction, you'll take more energy.
Well, if you had a force which was holding the glass down, you would and this is what Newton says. It's all about balancing these forces. In order for you to overcome that counterforce, you would have to apply a force which is at minimum equal to keep it in equilibrium or greater than to cause it to move. Just like for example, a shopping cart. When it's sitting there, it's not moving. You have to come and push it in order to get it moving. That's all. I mean, it doesn't matter whether it's now. It turns out that air, the molecules are pretty far apart, so it doesn't cause a lot of resistance over really short distances. A thicker liquid with greater viscosity would, but there's really nothing mystical here, and it has nothing to do with density.
It has everything to do with density because it's the medium dependent. You would agree if I had to take that same cup and throw it now in water, it will float. Because it's
maybe we should start with this. What are you defining density as? That's what I don't. Maybe I'm not understanding.
Like I said, as in simple terms, it's just the amount of stuff crammed into the object cubic centimeters. So the volume is the amount of stuff crammed into volume. If it's more compressed, it's heavier, it's denser.
Well, no, heavier, denser. Again, now we're confusing terms. Mass, density, and weight are three different things.
If you have more mass in a volume, it's denser, correct?
If you have more mass in what? I'm sorry,
volume. More mass in a volume, it's denser.
Yeah, density represents the amount of mass per unit volume. Yeah.
And if it's denser, it's got more weight than something with the same volume with less mass.
True. Two objects which are the same size or have the same volume, but one has more mass per unit volume would essentially have more mass than the other one. So it would, under gravitational acceleration, would weigh more.
Exactly. So you asked me, so I just explained it to you.
But still, it doesn't apply to the cup, though.
Oh, yes, it does. This cup has density to it. It's got mass.
Okay.
So this density of this cup is denser than the medium around it. That's why in some mediums you place it in, it either floats or it sinks because of its density relative to the medium.
Okay. What about in a vacuum?
It's still denser because now you have no medium around it. If you are taking the little bit of medium that can support it and you take it away, why would you expect nothing now to support it?
What do you mean support it? You see,
let me try and explain it this way. You've seen Brownian motion.
Yeah, of course.
Okay, so imagine Brownian motion now in a box. The gases are just moving all over the place. Now you've got a pebble in there. Okay, you've placed it on top in that box and it's going down, but you're still seeing all those gas molecules going around like crazy. They're hitting it, but they don't give it enough pressure to hold it up, so it cannot support it. The gas isn't supporting it, so the pebble falls. Now we do the same in a vacuum. You've got 1 or 2 moles bouncing up and down in that vacuum. Now you drop the pebble, it still drops. Why? There's less pressure to support it. Now let's take that same pebble and we do, like I said, with the Magnus effect with a leaf blower, and it holds it up because there's enough pressure to force that pebble to stay supported in the air.
Yeah, that I think, and when you start talking about Brownian motion, you got to be careful here because now you're talking about statistical mechanics. You're almost conflating two different fields of physics into one. It sounds really impressive, but it's not.
I was just trying to give you a visual, how can I say, understanding of seeing the molecules move. That's all I said with Brownian motion.
But see, you're introducing this idea of a gas. It's irrelevant. It's irrelevant.
No, it's the medium. Medium is relevant. That's
the medium doesn't even matter either. Why would the medium matter? Medium only requires when we were having like sort of like energy passing through it, like, such as waves. A cup is a cup is a cup, regardless of whether it's in air, whether it's in water, whether it's embedded in a solid. It's just a cup.
Let's do it this way. If the medium doesn't matter, let's take an anvil. You stick an anvil, and there in a vacuum, it's going down. You stick an anvil again in a gaseous environment, it goes down. Stick it in water, it goes down. Now, what happens when you stick that anvil in a pool of mercury?
Well, the mercury provides a force which keeps it up.
Great. So it's got enough pressure
Yeah,
to
counter
support
force.
it.
It's just like an airplane. I mean, an airplane
So,
goes up in the air because of lift. We're just talking
great.
about force here.
So the medium is so it is dependent on the medium then.
Yeah, but it doesn't deny gravity, though.
It does. It shows it's got nothing to do with gravity, only medium dependent.
If there were no gravity, it wouldn't just be the mercury holding up the anvil. The anvil would just sort of get up and sort of float away. Like,
You see what I said in the beginning of this chat, where I say your fundamental belief is you require something to hold you down because you believe if you have nothing holding you down, you would fly off into space.
no, we have
This
evidence.
is exactly this. No, this is exactly what I was talking about in the beginning.
Well, I think what you're talking about more. I mean, you can. So this is where the idea of conspiracy theories come in, and this is why. And this is why I don't. I'm not here to have a debate because you don't debate.
Chatting.
Yeah, you just chat about it because the problem is, as a scientist, we're required to follow rules, equations, stuff like that. Whereas the other side can just sort of make stuff up. Now, if you want to perhaps show that physics work in a different way besides these ideas of forces, that's fine. But within the construct of physics being forces, which all of the evidence shows that this is a way to model how the universe works, it fits. Like when you say adding to mercury, you're negating the fact that mercury itself is now introducing another variable, it's introducing another force. Density, again, you're conflating density, mass, and weight all into sort of one thing, and they're not the same. I mean, using your logic, we should be able to put an anvil in a vacuum. Should it be easier to pick up in a vacuum or more difficult? Would it weigh less in a vacuum or would it weigh more?
Less.
Why?
Because there's less pressure underneath it to help it.
But
I mean,
since weight, even though it's different than mass, but it's related to weight. Remember, weight is an object's mass multiplied by its acceleration. The mass of the anvil is invariant. Mass doesn't change.
Mm-hmm. I know, but that's why it's medium dependent.
Why would it weigh less? So what exactly are you defining weight?
It would weigh a fraction less because it doesn't have that gas hitting from the bottom. But then again, it would have the gas actually all around it. So yeah, like you said, it just cancels it out. So I'll
but it does. I mean, we can conduct this experiment though. It's pretty easy to do. We just stick an anvil in a vacuum, see if it floats.
It won't float. Why would you expect it to float? Because
see if it weighs less. See if its mass changes.
No, the mass will always stay the same. You would understand weight is simply just the pressure on a load scale. You know how scale works.
Are you saying that the gas is like pushing a weight down on the anvil?
Gas bombards in all directions constantly.
Yeah, I think so. You're again conflating forces with weights, and I mean, I get the logic. That's just not the way the universe works, though. It's
because you would understand.
I mean, yeah, if you eliminate, obviously, gas itself is matter, has a certain amount of weight, but relative to the anvil, we're talking about something negligible. No, the weight, the change of the weight doesn't change that much.
That's why I said I would concede that no, it wouldn't change because it would be hitting all of that. It's such a little bit of amount that to change, it wouldn't really change the weight. But like I'm saying, what is the weight? You know how a scale works.
Yeah, obviously. But
so a load
again,
cell. It's the pressure on the load cell. So it's let's for instance say this cup. My hand is the scale now. I've got a load cell in the scale. It's simply the pressure of the cup forcing on that load cell. That is what weight is. It's just a measurement of the pressure force on the load cell.
So now, what are you defining pressure as then?
Pressure.
Like if I ask, what do you mean by pressure? Like, what is how are you quantifying pressure here?
Like PSI, pounds per square inch.
Pounds per square. What is a pound?
Pound is weight.
What is weight?
Pressure.
I'm not trying to be pedantic here, but
yeah.
you need to define these things.
It's the density.
Weight is not density. Weight is not density.
What's weight then?
Weight is a force.
Exactly. Density is a force.
Density is a scalar. It's amount of mass per unit volume.
Yeah, the
Whereas
density of the object, but you don't understand the density of the object itself is a force because it causes a pressure.
no, density is not a force.
I think
I see. Okay, that's where the mistake is.
you see,
Density is
that's why
not.
I think, but I think that's where it gets to the confusion with you guys because you define gravity as the force, and the problem is you can't have a force thanks to general relativity. We
Well,
can define density as a force because this cup has a density to it and it forces itself on the scale, which gives its weight. So therefore, I can contribute saying its density causes a force. Well, you
okay.
guys can't
Yeah.
take gravity and say gravity causes a force because gravity is only an illusion.
No. Well, what I'm saying though is gravitational acceleration is a vector, whereas density is a scalar. So I think maybe that's where the
According to your
confusion is. See,
no,
density is not a. It doesn't. Density is not a
specific
force.
gravity. Specific gravity is scalar. Relative density disequilibrium is not scalar.
How so?
I
Show
just
me.
explained it to you. I
Show
just
me. Show
explained to
me.
you. Again,
Give
the
me an
cup,
example of it.
the
Like, how
cup
could density have direction?
if it's denser than the medium, its direction is down. Less dense than the medium, its direction is up.
What about a combination?
Then
By
it's
definition,
you've seen a density tower before.
a vector should be able to exist, in all of your Euler angles. Like, what direction does density point? Density is not a vector.
According to specific gravity, it's
Because
only a scalar.
mass is kilograms, right?
Yeah.
So you take the amount of mass per unit volume. Unit volume is only a measurement of length, width, height, right? That's it. It's not. There's no direction.
That density causes a force. It causes pressure.
Well, pressure is not. Wait.
Just like when a gas molecule hits something, it's the gas causes a pressure. It causes a force to push something. Exactly the same with any object. It's got density. It causes a force.
Well,
because
no.
it's dense. Yeah, because it's dense and it's forcing itself onto my hand now. If I had to take this cup and my hand and we had to go sit in the Dead Sea now, the cup will float away from my, and therefore the medium has the greater force. It's forcing it away.
Yeah, buoyancy, and forgive me, I always pronounce this word wrong. I know I'm a native English speaker. It's one of the weird words I have. Is a force, but not density. Density is not a force.
Specific gravity is not a force. I definitely agree.
I'm not talking about specific gravity. I'm talking about density.
Yeah, your density is specific gravity. Relative density is specific gravity.
That would imply that I could.
Model.
Based on your model. Based on that, though, one could say that okay. The density is 43 kilograms per cubic volume in the positive x direction. It doesn't make any sense. It's like trying to say the temperature is 57 degrees in the y direction. It's a scalar. It just doesn't make any sense. It's completely illogical. And that's probably where I'm getting confused. I think, again, maybe you're trying to say something. You're just using the wrong terminology.
Like I said, I've got conflating the two. No, I've got an actual mechanism that shows that the density of an object relative to its medium causes an acceleration. Therefore, it has a force, F equals ma. This cup is denser than the medium around it. Therefore, it will accelerate because the area around it, the medium around it, cannot support it.
So well, if it's not accelerating, it's not a force. If it's not accelerating, it's not a force.
There, it's accelerating.
So so how many newtons was the force?
I don't know, but the point right now is it accelerated, so it had a force to it.
Well, yeah, correct. It accelerated.
Okay. Because the medium. Now, if I had to do the same thing in water, a saline water like the salt water, it's not going to accelerate downwards. It will accelerate upwards.
No, not necessarily. But you're just talking about adding force together. That's
Remember,
it.
The whole point is you have a force to accelerate a mass. When it comes to gravity, there is no force to cause that acceleration. So you guys have lost the mechanism to have that acceleration, where I
you're
have an
jumping again.
actual physical mechanism which explains why it accelerates.
But it doesn't, because density is not a force.
Denser cup than the medium
Yeah.
accelerates due to being denser than the medium. So therefore it forces itself.
What causes it to accelerate?
It being denser. It has a larger pressure. The pressure is not enough to support it. Therefore, it's displacement. Archimedes' principle.
Yeah, no. Something is going to cause the acceleration. And the thing which does, ironically, your example, which you're trying to use, is predicated upon gravitational acceleration. Because that's the only thing causing it to move. If there was no gravitational acceleration, it would not matter whether you, like, let's put it this way. Hypothetically, let's say there's no gravitational acceleration whatsoever. Stuff wouldn't float. It wouldn't sink. None of that would matter. Things only, I mean, the thing which causes an object to sink, let's say in a denser medium, is gravitational acceleration. What causes an object to float is because you're overcoming that gravitational acceleration. But in both cases,
again, you don't have
gravitational vector is constant. It's a constant vector.
Again, you don't have the mechanism to claim that.
No, we do. It's called
general relativity. Specifically says it has no force.
Yeah, but now you're once again jumping into general relativity, which
what your gravity is. That's what your gravity is.
I mean, if you want to start talking about the cause of gravity with general relativity, these two things are totally separate. Remember, Newton didn't know anything about relativity. Einstein came up with general relativity to basically explain certain things which we observe, which just couldn't be explained with Newton. It wasn't that it was wrong. It just wasn't exact. It wasn't exact.
But that's the thing. Newton would explain gravity as a force. But
I mean, it's when he came up with the idea of a force. So he's like,
but even Newton doesn't have a mechanism for this force. It's just spooky action at a distance.
Whoa. Now you're talking quantum mechanics. What do you mean spooky action at a distance?
This is actually
totally different field of
no.
Yes, it is.
Newton specifically said he does not want to be ascribed to this force because of the spooky action at a distance.
No.
He found it absurd that
Newton knew nothing about spooky. You're talking about quantum mechanics. You're talking about quantum spin numbers, stuff like that. Totally irrelevant.
Which came
totally irrelevant. In Newton's time, he didn't even know any of that existed. He didn't even understand it.
He found it absurd that things can attract each other without having a mechanism to attract each other.
Well, it is absurd. There's got to be a reason for it.
That's why he found it absurd. Then C.V. Boyce came in afterwards, and he went and he decided to attribute gravity as a force to Newton, like 107 years or something after he died. All good and stuff, okay? Now it was seen that mass attracts mass, but there's no mechanism that links the two on why mass attracts mass. It's just there. It just happens.
Well, true. And again...
Okay, so you have no mechanism. Then came Newton and decided, hang on, I need to give a mechanism of why it attracts. And that mechanism is the fourth dimension, space and time bending. And the problem with that is it's only a concept, a mathematical concept that is not physical. It's only an illusion. As I was saying before, the Earth, according to the reference systems on general relativity, the Earth is the one accelerating constantly. Everything falling is the one that's not.
No. In both cases, you're conflating.
There's no mechanism for gravity. There's no mechanism for gravity that gives you your acceleration.
No. General relativity does show. It does show why. General relativity does show why.
Where I have a physical mechanism which shows why we have an acceleration.
Yeah, because of the curvature of space-time. I mean, like I said, that and it took us, until the turn of the 20th century to start to fully understand that, because Newton's laws couldn't explain it. But as far as Newton was concerned, he didn't know anything about spooky action at a distance and this and that. And in fact, the idea of not knowing the mechanism, only seeing the effect, is something which shows up in science all the time. Hence the difference between a law and a theory. I mean, we should also point out, based on Einstein's mathematics, an aircraft shouldn't fly. He didn't believe it could, yet it can. And Newton didn't know anything about space-time curvature or relativity or anything like that. But his equations of motion worked. But
like I said,
if you were to ask Newton why is a force mass times acceleration, he wouldn't know why. I don't know why, it just is. Then
I think Newton was.
He shows us why. And granted, there's still a lot of stuff we don't learn. Like, for example, when we come up with this idea of dark matter, what's causing the universe to accelerate? We don't know. We really don't know. We don't know what's causing that as of yet. But that doesn't mean we negate the whole theory, because all of this other stuff still
That's the problem. That's what I was saying.
Going back to like tectonics.
But that's when it comes back to when I said science is not, gravity is not scientific. You don't know the cause, therefore you don't have science.
Yeah, but we have to discover the cause. Now, we say the cause, the evidence points to general relativity. We don't know everything about it. I will concede. Like, for example, can we predict earthquakes?
I'm just saying, so we can logically then deduce, because gravity is not scientifically validated, we do not need to say gravity even exists.
No, that's absurd. That would be like saying, because we don't fully have the ability to predict earthquakes, we should deny that they exist. They do exist. It's there. It exists.
Like I'm saying, I can create a hypothesis, like I just did with the cup, and I experiment to show you what happens. That would be scientifically validated.
Well, I could design a building using Newton's laws of gravity, which will stand up and not fall down. Do I have to know what is causing gravity? No, I don't.
We can call Newton's laws of gravity Newton's laws of physics. It won't make a difference. It doesn't make it gravity. It's just a name contributed to the observations that he gave based on the physics.
Well, so I think...
Remember, there's no mechanism for your gravity. There's no science for the gravity. And you conceded that, you don't know what it is yet. So we can actually then concede based on logic and raw reason.
Well, no, we haven't. We just don't know it exactly.
So it's a belief then. You believe there is a gravity.
No, it's not a belief. It's based on empirical evidence, quantifiable evidence, which allows us to make
science.
That's exactly what science is. For example, let me ask you this. What do you think is powering your computer right now?
Electricity.
Electricity. What causes electricity?
Just electrons bombarding.
And what causes that? Yeah. Are you aware that that's also related to general relativity? Mm-hmm. Did you know that?
Yeah, but we are talking about gravity, not electrons.
I know, but I'm saying, are you aware that's what it is? We don't fully understand all of it.
I'm not saying you don't get. We haven't advanced in technology and stuff based on the belief of gravity. Like I said, your gravity can be called relative density disequilibrium, and it would be
density is something totally different. Density is something totally different, not even the same ballpark.
Okay, let's put it this way. Gravity would say the cup is accelerating due to gravity, correct? Now I'm saying the cup would accelerate due to relative density disequilibrium.
That would be wrong. That would be wrong.
Why is it wrong? I give a mechanism and why it's a force. You don't even know what gravity is.
Because what you're doing is you're redefining density. I mean, if you want, you're basically calling density now your gravitational force. So you're just replacing a term with something else.
How can I replace something that doesn't exist?
You're falling into the same thing, which is why I didn't want to talk about the flat Earth, which is a sort of false dichotomy. If it's not gravity, it must be density. Have you ever considered that? Okay, let's say, if you're not going to accept it's gravity, I'm telling you, fine, let's table gravity off to the side. I'm telling you that it's not density. It's possible it could be something else. But just because it's not this doesn't automatically make it that.
Sorry, I just want to
difference between why I can say it's general relativity and why I'm able to don't have the burden of proof to show otherwise is because they're predictable, quantifiable equations that will lead us to that conclusion. Those same equations don't apply to density. That's not how density works. Density, by definition, is not a force.
Okay, I want you there now.
You want to redefine density as a... Oh, sorry, there's a super chat. Sorry.
But I'll get back to your statement now. It says, Tony Whitcomb, thank you very much for your £20 super chat. He says, gravitational attraction is one way and buoyancy is the other way, depicting on an object and medium. One is real, the other one is fantasy, as clouds are not pulled to Earth in that medium. Thank you very much for your super chat, Tony. I 100% agree. And I mean, that's like I'm saying with my point to you. You guys take a mechanism which you don't have. On your gravity, this cup is only appearing to accelerate. It's not. It's now, if I'm dropping it, it's me accelerating upwards to the cup, apparently. It's only appearing to drop. That is your gravity. Now, based in reality, what do we observe? The cup is falling. I give a mechanism on why the cup is falling. Therefore, my hypothesis is scientific and validated, where you've made a concession that you don't know what gravity is, you don't have any mechanism for it other than a belief system. Just because physics and every technology works on the belief of this acceleration, which is there, doesn't make it gravity. You can call it unicorn farts. It will give exactly the same outcome.
Yeah, but I could say the same thing about your theory. I mean, you're just saying, oh, look, the cup falls, therefore it's not gravity. Again, you're confusing inertial. All inertial frames are is just a consequence of mathematics. The idea is that all equations are irreversible, meaning that, for example, what's on the left-hand side of the equal sign, you can reverse and you can switch them around. It's exactly the same thing. So if I want to say that I'm within the inertial frame of the cup, okay, I can model, change some signs around. Instead of negative, use positive. Okay, well, my hand falls up to the cup. Or I could just switch that around, say my hand is stationary and the cup falls down. Now, when it gets into gravity, now we have to start talking about something called, if you really want to get into Einstein stuff, we have to start talking about an object's rest mass, Lorentz transformations, all of this stuff, which is going to require a crap load of math. I'm not saying that I'm trying to avoid that discussion because, well, it's a lot of math, so therefore it's complicated. I'm just saying there's a lot of prerequisite stuff which we need to talk about. All you are doing with your argument is you're just redefining density as a force. So if you change what you define as a force, like for example, you said, I call it gravity, I could call it unicorns, I could call your pressure theory unicorns too. But the difference is your theory has no predictable equations, zero. Yeah. And it can produce no predictable results. And it also doesn't really make that much sense. I mean, like, for example, how does an airplane fly? Is it because of density? Does an airplane become less dense when it flies?
No, it's simply pressure.
What do you mean it's simply pressure?
It's pushing up again. It's aerodynamic.
Well, what about it makes it aerodynamic? I mean, why does an airplane fly? See, the thing is, in order for your theory to make sense, it has to explain all of these things.
Because it creates a low-pressure system, which helps it move with the friction of the air.
You're talking about Bernoulli's principle, which, by the way, Newton denied. Newton said that couldn't happen.
Good for him. But like I'm saying, physics, Newton, 100%. I agree with it. Newton, brilliant. That's how we get everything working today. It's F equals ma, true statement. But does that make the gravitational pull, as you call it, real? No, it doesn't. It just makes the acceleration real. Now, because we base our technology or understanding on this acceleration, and because you call the cause of the acceleration gravity, doesn't make gravity real. It makes it a pseudoscientific belief.
Okay, well, then I think where we're at is you're just denying that gravity is real. So, I mean,
no, you haven't provided me scientific evidence that it is.
That's not really an academic debate or discussion anymore. It's like, I mean, for example, I was having this conversation with somebody else. I deny angels. Okay, I say angels don't exist. I need some proof of it.
We can put this to bed then.
Now, there are plenty of people who would show me, look at all this empirical evidence that angels exist, and I will continue to deny it. But if I negate all of your evidence, saying, well, no, that's not true, it's because of this, it's because of that, then you're now talking about a belief. But to say that science itself is a belief is kind of a little bit silly, because the thing is, everything around you is based upon the scientific method. For example, when Faraday came up with these electromagnetic equations, he had no idea what relativity was. Yet Faraday's equations, when it comes to magnetic induction, and even just some of the basic, things about electricity, are still completely valid. It did not say why we have electricity. It just showed that you can make predictable results with this. Now, using your same logic, we should also deny that electricity is a force.
No,
just because we have to accept general relativity in order to explain electricity. So what's good for the goose has to be good for the gander. And And that's what I'm trying to say. The flat Earth model gets into trouble because it tries to now disprove or deny whole fields of science. And that's when it gets itself really into trouble.
But that's
Because
the thing, your field is not science. If you want to give me a hypothesis and scientific experiment that validates it as science, I'm all ears.
well, and again, I'd have to ask yourself, I mean, could I actually give you, I mean, is this something which you would have to conduct the experiment on your own to believe it? Like, I mean, there's plenty of evidence to show. I mean, there are videos of this or that. I mean, of course, but just like, pictures of us landing on the moon, you can deny the moon. If you're just going to deny the evidence, but I mean, that's fine. That's your right to do so.
But that's what science is. It's simply an empirical method to figure out the cause for effect. So if you're saying gravity is scientific, it contradicts your statement that you say you don't know what gravity is.
Einstein's field equations are incorrect? Let me ask you that. That's really where we're going with this. Is if you're going to deny general relativity, we need to know what about it do you deny? How are the equations incorrect?
It's based in a mathematical concept of the fourth dimension that we cannot even observe.
We can. It's called a four vector. It's easily. I mean, that's not that big of a deal. It's
okay. Tell me, how does a two-dimensional being observe things in three dimensions?
That has nothing to do with what we're talking about here. Like, what is it about?
We are three-dimensional. Correct?
Hold on. You accept force equals mass times acceleration, but then 100%. You deny Lorentzian electrodynamics. Why?
Never said
that is incorrect.
I never said I deny it. I'm talking about specifically on the point now. You make a claim that gravity is scientific.
It is.
Yet you made a statement that no one knows what gravity is. Therefore, it cannot be scientific. Because to be scientific, it means it had to have the empirical evidence gone through, hypothesis, and experiment, which that means you do know what gravity is.
Yeah, so you're falling into the trap as if because we don't know everything, that means therefore none of it exists, and that's just not true. There are still, I mean, any scientist who comes up and says I know everything doesn't know what they're talking about, because honestly, if we knew everything, then I would be out of a job. But the thing is, what we do know about Einstein's general relativity, the observable. The equations yield observable and predictable results. Is there still some unknowns? Yeah. I mean, look at what we did at CERN, trying to find out what actually causes mass. I mean, what is mass to begin with? And that was the search for the Higgs boson. We knew that it existed, but before we found the Higgs boson, it would be ridiculous for us to say, okay, because we haven't found the Higgs boson, mass doesn't exist. And that's just not how the world works. In fact, using the example of airplanes, I mean, we knew how to fly before we knew why airplanes flew. Does that make sense? We knew how to fly before we could explain exactly what generates lift.
Yeah, people are looking at birds and saying, how are we going to mimic that? Yeah, but that's not my point. Again, we get back to my point. If we are three-dimensional beings, okay? General relativity is based in fourth dimension.
Well, it adds space-time. It adds space-time.
How do we observe something in a higher dimension?
Oh, that's easy. Okay, so I see where you're going with this. So, yeah, I mean, we do exist in a three-dimensional universe. And for us, we perceive time as a constant. If it's a constant, we don't consider it a dimension, right? And it just moves in one direction. However, because of special relativity, we know that time is relative. And it comes into this concept of what we call space-time. It's actually really not that complicated. But once we discover that, look, time cannot be constant, it does add an extra dimension to it. The reason why we say we live in a three-dimensional world with constant time is if it's constant, we can just remove it from the equation. We can just get rid of it. But in this case, now time is no longer a constant. It's relative to whatever inertial frame you are in. And so it becomes a four vector. I mean, we still perceive it. And again, I mean, here's an example. I know what you're going to say. You're probably going to deny its existence, but GPS works because we understand what four vectors are, that we can do these calculations in four dimensions. So
I'm not saying you can't use time as a reference. I mean, that's also just
that's your fourth dimension there. I mean, to put simply, it's not exactly just time. It's called space-time, but
the problem when it comes to space-time, you're redefining what time is. As you said, in 3 dimensions, it's a constant. In fourth dimension, it's no more a constant. So
Yeah.
how do you go and observe time not being a constant?
Well, because then it gets related to velocity. I mean, at a low enough velocity, time is a
Still a
constant.
constant. It's still constant.
As you accelerate closer and closer to this upper speed limit, which is the speed of light, well, the universe gets kind of weird. Time is no longer relative. Something else must change, because if we say that nothing could go faster than the speed of light, something else has to make up for it. And it actually wasn't Einstein who came up with this idea first. It was, once again, this person named Lorentz. There's some debate about whether he should win the Nobel Prize or not. It really started showing up when we started dealing with electricity, because electricity is something which travels at a very high velocity, starts approaching the speed of light. And it's called this thing called like Lorentz transformations and whatnot. But it was Einstein who showed why. So and that's why then we had to redefine gravity, and it came down to it was the precession of Mercury, which all of like Kepler's laws of orbits coupled with Newtonian's laws couldn't explain Mercury's precession. And then once we introduced this idea of general relativity, it's like, oh, boom, we can make predictions. So now we can tell you where the orbit of Mercury will be, I don't know, 1,000 years in the future or whatnot. I mean, that's all it is. The thing which I found on the internet, and especially among those who, here's the problem with science. Science is very inaccessible. And I think we as science educators haven't done a really good job of making it accessible to people. And I think we make the mistake of then when people say things, we want to shout them down so quickly and say, oh, you're so stupid. You don't know what you're talking about. And that's a failure on our part. But the fact of the matter is, I mean, the science works, and science does not have to conform to our beliefs, which actually leads me to another point, which I really wanted to ask. And, I see the chat.
100% agree. I 100% agree.
Why deny science? How does it benefit you to deny it?
We first need science to deny it. That's why I'm trying to.
Well, why?
But that's why I'm trying to push you on, because I'm trying to explain to you your general relativity, your whole gravity belief is, excuse me, a belief. It's pseudoscience. So therefore, it's not science.
No, there's empirical evidence and repeatable, predictable results. That's what science is.
Remember, you said earlier you don't know what gravity is, correct?
We don't know what it is, but we can make predictions. Just like we don't exactly know the mechanism of flight. Would you deny that airplanes fly? I mean, no, we wouldn't.
Airplanes fly. Scientifically, airplanes can fly. We're talking about gravity.
We don't know exactly why.
Gravity is.
We don't know exactly why.
You see, gravity is scientifically, empirically validated. So that means you have to have a cause for it. So if you don't know the cause, it cannot be scientifically validated. But that means it's pseudoscience. It's just a belief.
But you're saying it's not scientifically validated. I guess maybe you misinterpreted what I said.
Then give me the hypothesis and
maybe I should clarify that there is a lot about gravity which we don't understand. What transmits the information of gravity? For example, how does planet Earth know that it's in orbit of the sun? Yeah, how does it know it? Is this idea of like information?
It's not sentient, so it doesn't.
Just because we don't know, what the graviton is, doesn't necessarily, if that's even what we're going to call it, doesn't actually mean that we then deny all of gravity. Because just like, for example, plate tectonics, just because we cannot tell the exact way to predict an earthquake, if we knew all of the variables affecting plate tectonics, we should be able to predict an earthquake. But the fact is, we don't know all the variables. But that doesn't mean we're going to say that, well, since we can't 100% predict earthquakes, that means that plate tectonics is just a belief system and we're going to throw it out the window, or evolution or germ theory or any of these. I mean, that's just not how the scientific method works, because it doesn't lead to any progress. I mean, there's still a lot to be done. For example, we all accept that a proton exists. We all accept that. Do we know exactly what's inside of the proton? Well, then we found quarks. Right now we know that exists, but do we know what those are made of? Well, now it gets a little bit more complicated. What exactly makes up the proton? Well, it gets complicated. What gives proton its mass? It's a little bit complicated. We don't have all the answers yet. We're not going to deny that protons no longer exist just because we don't know.
But I mean, that's what I want to ask you. Can you provide me with the actual scientific hypothesis and experiment that showed gravity to be scientifically validated?
Newtonian gravity, yeah, Cavendish experiment. Boom,
That's
done.
that's an experiment. Can
Yes,
you
it
give me
is.
the IV and DV, please?
It is an experiment. Now you're getting obsessed with semantics, independent variable versus. I mean, using that, it's like, well, can I deny that if I take an object, drop it at various heights, and then plot it on a simple graph to get a linear relationship, I should be able to find, velocity. It's like, I don't understand the question.
Okay, let's put it this way. You would understand the
General
Cavendish.
general relativity experiments are complicated.
No, but we're talking about Newtonian gravity now with Cavendish because it's claimed mass attracts mass due to the Cavendish.
What do you think the
experiment.
Cavendish experiment is? Maybe there's some
It's showing
distinction. Maybe you don't fully understand it.
It's torsion twist due to torque.
Okay.
Even the data shows that, correct? Because he was trying to measure Earth's density.
Okay.
That's where you got your constant. That's not an experiment. It's a demonstration.
Yeah, well, you're talking about capital G.
It's a demonstration of torsion twist due to torque.
Gravity. You're talking about capital G, right? Newton's gravitational constant.
Mm-hmm.
Yeah. Which again, one of the things with Newton is they're very good approximations. Force equals G m1 m2 over r squared. It doesn't really tell us anything about why. So, in fact, not to get this conversation too convoluted is, again, we should still define certain things. And I guess a simple way to do it is Newton shows us, okay, these are the effects of gravity. Einstein shows us why. But the two, we're trying to reconcile the two, which comes up, these ideas are called grand unification theory, all of that, corresponding with the standard model. And that link, yeah, it's still up for debate. It's still up for debate, among many other things. I just think to flat out deny it doesn't really, I just don't understand why.
But I'm not denying it. Like we say, talk about Cavendish now. You agree the data is simply just torsion.
Let me ask you this. How would you design a bridge without gravity? Would you be able to design a bridge so it doesn't fall without using Newton's equations?
You just change the G to uniform faults. It doesn't matter. It gives exactly the same thing. Remember what I said in the beginning? I agree 100% with Newton. He was explaining, based on observation of everything in the day, how our physics works. The problem is you take that acceleration of what we observe and you give it a belief that something is pulling it down. That's a belief. It's not scientific. It's a belief.
Well, nothing's pulling it down. It's rather acceleration. But again, semantics.
Great. So yes, I agree. Nothing's pulling it down, and that's why general relativity is also saying nothing's pulling it down. So now, based on general relativity,
why do we believe this though? Why?
It throws away F equals ma. So you got to choose general relativity or F equals ma.
Then why is it that this is accepted? That's what I don't understand. And it's
because it's the consensus. The consensus is based on pseudoscientific belief.
Well, the consensus is based on being able to do an experiment, peer review, predictable results, blah 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 blah. I've heard many different theories as to why. I mean, I as a scientist, if I could show that gravity does, put it this way: if I could show that Einstein was wrong, if I could actually show that, I would be the happiest person around. I would win the Nobel Prize, but I can't. Nobody else really can. There's still stuff left to discover, which falls in line with the theory.
Eric Delinde, entropic gravity, it shows Einstein wrong. There's a lot of faults in Einstein's equations, by the way. There's a lot of people that you can look up that actually show why general relativity is wrong.
Well, what do you think?
But they get pushed aside because it's the consensus.
Well, science is unforgiving. Science is based on this idea of peer review. There's been plenty of stuff which the scientific community has considered consensus, which has later been shown to not be true. For example, is the universe expanding? Again, this happened at the turn of the century. Most scientists believed that the universe was eternal. It always existed before, it always exists past. Now, there are many scientists who had a problem with this because how could something have no beginning, have no end? And then the empirical evidence led us to show that, no, look, the universe is accelerating. Now, there's still questions about that. There's still questions about that. What's causing it to accelerate?
I would actually wanted to ask you. You watched my debate against Mark Reed, correct?
Was that yesterday?
No, that was FTFE. Against Mark Reed, we were talking about why NASA is deceitful.
I saw parts of it.
Okay, but you saw my argument on the first law of thermodynamics.
I did not. I'm sorry, I did not.
Okay, because he couldn't answer me. So I want to just want to, out of just interest sake, to see how you would answer it, because I mean you are an educator and stuff. You're obviously very familiar with the laws of thermodynamics.
Yes.
Okay, so the first law of thermodynamics, you understand nothing can create or destroy itself. It can only be transformed or transferred.
Okay.
So how did your universe originate?
Well, now we're talking about cosmology.
Well, we got matter. All this matter.
So you asked me what happened before the universe?
But that's what I'm saying. How would you answer it if I had to ask you? Your heliocentric model derives from the Big Bang, the origin point. Now,
wait.
How?
What do you mean by heliocentric? The sun is at the center of the universe?
It's heliocentric. It's called heliocentrism.
Yeah, no. I know the heliocentric solar system. You know, the sun is at the center of.
Okay, yeah. Look, we know that's just the dance, but like saying the globe model. Okay. Now, your globe model is based on having an origin point, which is seen as, thanks to the CMB, the Big Bang. Correct?
Well, CMB is a cosmic background radiation, and no, it's not necessarily predicated upon that, because remember, we knew that the Earth was a sphere before we had any idea about the Big Bang. The two don't necessarily have to be
I'm
the
not
same.
worrying about the shape of the sphere. I'm talking about the origins. That's why we're talking about the first law of thermodynamics. Can you explain to me how, based on your model, it can defy the first law of thermodynamics to be able to create everything we see today?
Okay, well, I'm still not following the question, because you're asking me what happened before the Big Bang and how it fits in with a heliocentric model and a sphere. These are three different things. Are you asking me what happened before the Big Bang? What caused the Big Bang?
Yeah, what caused the origin of life?
I have no idea. No idea.
Great. That's awesome. Yeah, that's all I wanted. Because
no, we really don't. I mean, and this goes back to the idea of, as a scientist, we have to make the assumption that we exist within the universe. Since the universe is space-time, asking me what happened before time is illogical. It's kind of like if I asked you on a two-dimensional map to show me what exists at 91 degrees longitude. It doesn't make sense. Or, what is the circumference of a triangle? It's illogical. What caused the Great Expansion? We don't really know. We really don't know.
Yeah, because it defies.
We would have to step outside of the universe to look within the universe to see what caused it. We don't know.
Yeah.
And I'm not going to pretend to be able to solve that debate here today.
Yeah. No, I was just very interested to see how you would answer it, because how Mark was answering it was, he's calling it quantum collapse and stuff, and not understanding that quantum collapse still requires something to be there to collapse in itself, because it's a wave function.
What happened right after time started? Well, now we can start talking about it. Then we start seeing evidence, like, for example, cosmic background radiation. And now, just recently, as of 10 years ago, we were able to look back even beyond the cosmic background radiation using a project which happened in Antarctica called IceCube. And I think the paper won a Nobel Prize. But what happened before? Where did this energy come from? Hell if I know. I don't know. I have no idea.
So that's one thing. That's one thing I always want to challenge everybody, especially atheists. If you deny that there's a supernatural being, like a God who created, who's above nature, then you have to have an answer for how nothing can create itself, because it violates nature. So that's just one thing I wanted you to think about.
Yeah, which is why I think I said this earlier, that how especially the Catholic Church really liked the idea of the Big Bang, because it really did.
The priest, he created.
It pointed to a place of creation. Then you can say God said, "Let there be light." Whereas before, the universe is eternal. But you ask what happened before time just doesn't make any sense, because without time there is no before. And here's where I would agree with you. It gets a little bit pseudoscientific and more philosophical. Like, is something out of nothing, then we got to define what nothing is. Is nothing the absence of stuff? Then isn't nothing itself defined as something? Yeah, I don't even want to go there.
No, nothing doesn't actually. If you take it scientific, nothing doesn't exist. There's no such thing as nothing.
Yeah. I mean, I was talking about this in your chat last time. The concept of what exactly is nothingness.
Yeah,
but kind of weird.
But I have to say, man, I'm enjoying this chat so much with you. It's really
I appreciate it.
It's really awesome.
I do have to. Oh gosh, so it's already 2:00 my time. We started what 12:15.
Yeah, we've been going on for a few hours now. 2 hours.
So thank you for having me on. I hope everybody will vote yes. I'm more than welcome to come before, and maybe each one of us can come with some answers. The one thing which I'd recommend, and we're guilty of this too, as scientists, especially from the university, we tend to try to look down upon people. It's, like, oh, you're so dumb, you don't know what you're talking about, and label people who don't understand science as ridiculous. And I do see, just based on the chat on the other side, everything becomes this really big, silly personal attack, really based on nothing, really on nothingness. And that's not how scientific inquiry is done. I mean, ultimately, one should be able to say that the ultimate goal is we just want to figure out why. I mean, fundamentally, all of us are asking the same question, which is, why are we here? What is all of this? What is the meaning of it? And there is rigorous debate on each side about it. The thing about science is, it can be cold and unforgiving. And I think as educators, like, for example, I lack the words to explain to you general relativity without starting to go over Einstein's field equations, which then makes this concept inaccessible to the majority of people. And we as humans just naturally distrust people. And I would argue, science has been used to do a lot of bad things. Scientists, we sometimes get treated like gods, but some of them are not perfect. And and this permeates through everything, like the vaccines, COVID, plate tectonics, evolution, genetics, all of that good stuff.
I would actually like to have a chat with you maybe sometime on evolution versus creationism. I think that can be quite interesting, because you're probably for evolution, correct?
Well, it could, but you see, the thing is with that one, I'm not qualified. I'm not an evolutionary biologist. I will say, though, as a scientist, I understand why we accept that theory, but I wouldn't be able to answer specific questions about it because it's not my field.
Yeah. It's not my field. Okay. If you don't mind me asking, what more or less is your field there?
So I'm a nuclear physicist. I do experimental physics. I do hadron spectroscopy, or to put simply, I look at the structure of the proton. Okay. So we try to figure out, and to make a long story short, we take electrons, bend them to generate photons, slam them into a stationary protonic target, and then see what the hell comes out. Yeah. And then try to identify energy levels of these little tiny particles.
So it's based on the quantum eraser, this double slit.
Oh, well, a lot of it is quantum mechanics. For example, we have to use relativistic kinematics. So since our photons are traveling close to the speed of light, we can't just model them as three-dimensional, like actual three-dimensional objects. We have to model them using what we call four vectors. So X, Y, Z, and time itself.
It's quantum. Yeah, because it's quantum. It has to be in all places at once. So.
Now, quantum mechanics is kind of fun. I know you mentioned spooky action at a distance. Mm-hmm. It's something which I know quite a bit about. I don't know what would be easier, to explain quantum mechanics or to explain Einstein's field equations. I don't know. Probably
they're both complicated.
Full disclosure, I know a lot more about quantum mechanics than the last time I did Einstein's field equations was in grad school. So that doesn't really show up that much. I'd have to research how to even do the math, because like, how we use math, has plus signs, divided, this. There's this thing called like Einstein notation, which uses totally different symbols. And like I said, it's been at least 15 years since I've ever had to solve a problem like that. But But it's complicated. It's complicated. But anyways, thank you for having me on.
And it's awesome having you on. It's awesome having you on. I really appreciate it. Like, well, I'll definitely want to do this again. I mean, I think you agree. We can have a very nice discourse with each other. We don't really talk over each other or get heated or anything. And
yeah, I agree. And there's really no reason to get angry because and I have a rule on the internet. I believe me, I'm sure you can find some videos of me losing my temper on the internet. We've all done it. We have all done it.
Definitely.
But remember, the rules of the internet are he who rage quits first loses.
I think that was FTFE's plot last night, trying to get me to get angry and rage quit. But at the end, I was just like, I don't give a damn, and I'm sitting there like.
Yeah, and that's why I don't have debate. We all know the arguments each side. It's rather to have a discussion, and maybe somewhere in the middle, somebody will learn at least one thing, just something, maybe something small. Like maybe somebody in the chat had no idea that general relativity was related to Einstein's field equations. Maybe they're going to go look that up. Who knows? Who knows? Maybe somebody will learn something.
Yeah.
Anyways, thank you. Thank you for having me on.
Thank you very much for your.
I'll see you later.
Thank you very much for your time, mate. Cheers, mate. Bye.
Cheers.
Cheers. Okay, guys, that was awesome. I really enjoyed that. It was awesome to actually have an actual discussion with an actual PhD. Yeah, obviously you could see we weren't really agreeing on most things, but I think I got my argument through quite a few times like I needed to. I put the StreamYard link in for anybody that's wanting to come into chat for a bit. We can have a bit of a carry-on show to see if anyone wants to chat. Thanks again, Nik, for coming. I really appreciate it, mate. You rock. Yeah, I'd definitely like to do this again sometime. And the reason I enjoy it so much is because it actually feels like I was having a conversation with a grown-ass person, if I can put it that way. Yeah, so I really appreciate you coming in. It was awesome. So anybody want to come in and chat? I'm sticking the link in for you guys. Please do come. I want to say thank you again, Tony, for your super chat earlier. It's really appreciative. And if you guys don't know, like I said in the beginning of the stream, I am going to get my mic and processing unit soon. So then the sound issues will be a thing of the past. I got my green screen. I tried to use it a bit with this damn webcam, but it looks rubbish. As you can see, it's still fuzzy and stuff. So I think if I do use the green screen, it will be done in the daylight, or when I've moved to the studio and I've got myself a new webcam, I will do that. Yeah, even Rachie says, glad you caught that, Flat. So if he does try to make people rage quit so he can act like he won and ran away. That's how their tactics work. That was exactly the same when I had Conspiracy Cats on that time. That's why they just overtalk me as much as possible. But I'm too much seasoned into this topic to really give a damn on how they treat me. As long as I get the argument through, that's what counts. Yeah, Nik is a very nice guy. I've got nothing against Nik. And I think he's halfway there to being logical. Yes, he's still got cognitive dissonance, like I was trying to explain today. How he was contradicting himself with some stuff. But that's how it is. And I really, really appreciate him coming on. Obviously, he can't really change his viewpoint because he's an educator. If he had to change his viewpoint, they might sack him. Look what happened to Brian Mullen that time, guys. So, yeah. But yeah, if Brian Mullen is watching this, mate, we do miss you. You had some awesome content. And it was good to see so much people on stream. Really, really appreciate everybody. You guys rock. Please do share the show. I'm going to set this in Element as well, because why not? Come in and chat, guys. Be great to see anybody come and chat. Good. PJ, you want to come in a bit and chat, mate? Anybody? Or should I open the Discords for you guys? I don't know if your Discord's really going to work very nice. Yeah, Glenn, I 100% agree. Even if Nik Volt doesn't change his position, he still makes a great science discussion. I agree. I think there were a lot of good points brought up from both of us. I think it was nice and cordial. We could make our arguments presented. And like we said, it wasn't a debate, it was just simply a discussion. And I think he realized that I'm not actually some guy that just doesn't know anything. Otherwise, I wouldn't be chatting like I am. Okay, so nobody wants to come on. That's sad. Come on, guys. Someone wants to come on. Has to be someone. Otherwise, we're going to have to probably go and look at some videos on YouTubeness. Not sure if we should. Up to you. Let me know. Do you guys want to come in? Chat. Okay, let me maybe share my screen. Share screen. Present. Entire screen. Okay. Share. Okay. Let's look around what we can. I saw Dave McKeegan brought out another video recently. Oh wait. I'm gonna show you. STST. This guy. He thinks he is such a clever dude. Why is it not working? Okay, let's reboot this. STST. This is this one. The one he released today. Okay, let's download it because it's going to be much better to download. YouTube download. He thinks he's so clever with his arguments. In the meantime, he's showing his total ignorance, as usual, to the whole subject. I actually commented to him this, guys. Seems you have no idea what conduction is. Please stay a globe earther. I would be embarrassed to call you a flat earther. And that is true, guys. I would be embarrassed. Oh, PJ is coming in. Hey, PJ, how's it going?
Yeah, good. I wondered whether you noticed me. Yeah, I was an element at the start of the show, but I didn't realize you were going straight into the conversation with Nick. So I was waiting for a bit and nobody to turn up. Everybody's an element at the minute. Michael, Paul, Hama.
Should I open Element?
If you can,
I
can
do
you
have Element
open?
I do have Element open, but I don't. Let me join in the chat.
Can you do it while you're on StreamYard, can you?
It should, yeah. There we go. Hey, guys, can you hear me?
And everybody's in there as well. Right, I'll go back to StreamYard. I'll go back to Element.
Yeah. I'm in Element now. I don't know if they can hear me, though. Michael? Divergent, you guys can hear me? Hey, how's it doing, Divergent? Great to see you, mate. Yeah, he's coming over to you guys now. Sure. Okay, I'm just gonna stop sharing quickly. I was about to show a video from from STSE. Today's video that he showed. I was like, what the whoop? So yeah. Definitely. Yeah. No, definitely. But like I said, with Nick, he's always welcome because he's very cordial. Yeah, we do have our disagreements, as you saw, but I think I brought my arguments quite plain and simple that he had himself backed in a corner a few times there. So maybe hopefully I gave him a few things to ponder on, that he would actually go and sit back and think about it. Yeah, doesn't matter, even if he doesn't change his mind. I mean, yeah. And I mean, like I said, we've got a mechanism that can be scientific. They don't have a mechanism, so But now I'm going to move on to this numpty. Yeah, and this guy I'm going to call a numpty. Flurfs think the ISS should melt. Yes, according to physics, it should melt if it's there, if you ignore where it's placed at. So yeah, so for this video, we're just going to beg the question a bit and say, yeah, okay, the ISS is going to space, okay? We know it can't go to Narnia, it never can, but let's just beg the question for a bit, just based on physics, and let's see how idiotic this guy's argument is. You guys ready? Spotty. Can you guys not hear Element? Would you guys maybe be able to, rather than come into StreamYard then? Thanks. Yeah, if it's not going to work in Element, then I think it's going to be better to come StreamYard. No stress. I understand with you, mate. No stress. Okay. No stress. Okay. So I'll chat to you later, Michael. Cheers. Yeah. Yeah, definitely. I'll chat to you now once the stream's over as well quickly. How's that? Okay. Sure. See you now. Yeah, guys. Sorry about that. Okay. PJ's back in here. So they said they couldn't hear anybody in Element, so.
I thought so. I mean, we could hear them there, but they obviously couldn't hear us in YouTube.
Yeah. Tiger Bear, I'm off to watch Spaceballs 2, The Search for More Money.
Is there a Spaceballs 2?
No, I don't know. I think it's a joke.
No, I was going to say, I can't remember a Spaceballs 2. But there maybe was, I don't know.
Okay. You guys should probably see this on screen now. Okay, I'm going to press play. His intro is always the same nonsense, but yeah.
Yeah, hey Moomin, it's the Scootinator now. Oh yeah, Alan just said it. There's no sound coming through for that video. Flats.
Yes, mister. I can hear you.
There's no sound coming from the video.
Nothing.
No. They can't hear it in YouTube, and I can't hear it here either.
Okay, guys, then it's not going to work. Sorry. But anyway, his argument is simply, he says, why doesn't the ISS melt in space? And his demonstration, I'm going to mute him. So I'm just going to talk with, okay? So his argument is, remember, because aluminium and things should melt at a certain degree, correct? Every metal. Now, in space, in the thermosphere, it's said to be way hotter, therefore it should melt. So his argument is, we are dumb because we don't understand that there's no air, so therefore it cannot have a thermic reaction. Where the idiot doesn't understand there's such a thing as conduction. That's how idiotic this guy is. And look how he demonstrates it. He takes his, preheats his oven to 100 degrees, and he opens up and sticks his hand in. He says, see, I can feel it because there's air in the, in the oven. Because it's heating the air up. And he says, well, you see, let's take water, do the same thing, boiling water. I'm not going to stick my hand in there because it's going to burn me. Now, in space, there's no air. So therefore, it can't heat it up. So he doesn't understand what conduction is. That's how idiotic the guy is. Let's do this. I'm going to do this. Yeah. I think.
Right. Can I just say, yeah, Moomin, you can stick to Shankinator if you. I was going to say Skankinator then. Skank. Oh goodness. No, you can stick to Shankinator, but it was Alan Norstrand that made up Scootinator because I've got a new scooter. But yeah, you can stick to Shankinator. I like that as well.
Okay.
Yeah, let's go on.
You can see my screen. Okay, so on screen, It's the ISS. They're saying radiators. How does a radiator work, guys? Do you know, TPJ, how a radiator works?
Yeah. The water, well, the water radiators, the water goes through it and then produces heat. It radiates heat.
Yeah, but how does it actually work? It's simple. You got the water reservoir, and the
Oh,
water
right.
travels through the fins. But now, as it's traveling through the fins, there's air currents through those fins.
Oh, right. I see what you're saying now.
And it transfers that heat to the air currents. And that's why it gets colder as it travels through the radiator. Now, in space, if there's no air to get the air currents through the radiator, how is it cooling down? Where is it dissipating that heat to? It needs the air to dissipate the heat into for the radiator to work. Hey, Trinity 4, glad you could make it. Good to see you. Yeah, conduction and convection. Exactly, Rachie. So a radiator, let me do this, radiator of a car. This is because it's just a normal radiator. That's how they have the radiators. I want to see if we can get a good picture of the fins or something. Radiator close up. There we go. It's got these fins. These fins is where the air travels through. It's got the water going through these channels, and these fins are simply there for the air to travel through those fins. If the air is traveling through those fins, it transfers the heat to the air around it. That's why always when you drive your car for a long time and you stop and you take your hand in front of the radiator, you feel the heat around it because it's transferring that energy into the system around it, thermodynamics. Now can someone explain to me how the ISS has a radiator in space without air around it?
Well, yeah. It doesn't make sense at all, does it?
Oh, I didn't even add it to stream, guys. Radiator close up. Sorry, guys. I thought I had it on screen. As usual, I don't have it on screen. There we go. That's the fins. It should be on screen now. You got your reservoirs where the water's running through, and then you got these fins. So these fins, the air goes through those fins. They travel through it as the water goes, and it cools it down because it transfers the heat energy to the gas, air. So how does this work?
Flats, can I just ask? Somebody asked me a question. Mr. Groovy House, he's asking if you can see his comments. Just I don't know if you can see his comments.
Yes.
He's asked me to ask you. You can't see them.
He says it uses radiative cooling. And I'm explaining why the radiative cooling doesn't work in space.
Right, okay.
If we beg the question.
Okay.
Hey, Adam Meekin, good to see you, mate. Thank you for coming. Yeah, Trinity 4 guys has an awesome channel. If you haven't already, please do subscribe. So yeah, like I said, we're begging the question, and just based on how radiators work, it would not be able to work in a vacuum. Simple as that, because the radiator itself will melt because it can't transfer that energy, that heat to anything surrounding it. So therefore, melt away. Yeah, so STST, it's simply just conduction. The problem with STST that doesn't get, when it comes to, let's say, anything in the supposed space, it's much hotter up there in the thermosphere. I think it's in like, what, 2000 degrees Celsius, over 2000 degrees Celsius. So if the sun is giving radiation onto the metal itself, it's conducting all that heat energy into it. It should be a pressure cooker inside the ISS because of all that heat energy, because it's transferring all that heat energy from the aluminium inside to the gas that's in there for them to breathe. So they would be burning up and the ISS would melt. This is all based on their model, guys. So yeah, space is fake. You can't go there. This is just begging the question just so we can have some fun at the idiotic Numpties. Yes, radiators never work in a vacuum, Alan. Why do you think when you go on a dyno, they put a fan in front of the intercoolers and the radiators? That's so funny. Oh man, very funny stuff.
Yeah.
And all we get from the normal trolls, flats, you have no clue.
And they had like a rock
Break
flats,
about
which is shocking. You haven't got a clue. Like you don't know nothing, flats. You're so stupid. You know that.
Yeah. Okay. Then I can tell him this. Why don't you take the radiator out of your car and see if it's going to function? Yep, at high altitude, radiators lose efficiency. Why is that? There's no air to go through the fins and therefore cannot cool it down.
Exactly.
Adamican,
Nothing.
I'll ask again, given that absorbed solar energy is not able to be dissipated if no air is there to conduct it away, is it hot air that causes sunburn? Let me read that slowly. I'll ask again, given that absorbed solar energy is not able to be dissipated if no air is there to conduct away, okay? Is it hot air that causes sunburn? That's an interesting question. No, I wouldn't say it's hot air. I would say it's simply the energy from the sun directly to you. But the air does give magnification, though. That's why when you usually you have more sunburn on an overcast day because of the magnification due to the atmo. So it's like a magnifying glass, you could say. And that's also another point, Adamican. The solar panels on the ISS would also melt. Because what are solar panels usually made of? And that's going to be absorbing all that sun's heat energy, and there's nothing to dissipate the energy. As you said, it would melt away. No, radiation does not require a medium. I agree, no propagation needed. Transfer of energy requires a system or medium. But it's good to have you guys aboard. I can't believe it's already 11:30. Is that it for the stream? If you guys missed the discussion with Nik Volt, I do really advise you to do watch it from the beginning because we had an awesome discussion. Okay. I'm going to invite again. He says no propagation needed. What does that mean? You know what propagation means, Mr. Groovy House? Let's say you climb in a swimming pool and you create a wave. No water, no wave. The wave propagates through the water. Simple as that. There's the link if anybody's interested to come and chat a bit. Trinity Ford would be great if you maybe can come in and talk a bit. So you can explain to everybody what you actually do with your street activism and stuff, because it's really cool. Who's Joe Joyce? I have no idea who Joe Joyce is.
I'm about to ask that, Flats. Who the hell's Joe Joyce?
But yeah, that's very interesting stuff. I'm hoping to see maybe a Sean Hawkins stream on tonight, because you know that guy. That's when show's dumb again.
Oh yeah, he was so obnoxious tonight. He got timed out every time he come back in. He was just so obnoxious.
Because it's usually he says a statement, and then the next sentence I say literally says the statement and debunks him. It's crazy. Head like rock. Who are you to make declarations without any understanding of what you're talking about? Self-reflect. Get OFG or the Dunning-Kruger peak. What is he talking about? I don't talk about stuff I don't know about. If I don't know about something, I'd simply tell you I don't know about it.
Exactly.
Flataholic says heat can transfer in a vacuum. Is that so? Show me how the heat is going to transfer without propagation. We've had Action Lab actually melting things in a vacuum because it couldn't transfer the heat. He's had that molten ball. Obviously, it cooled down as the heat dissipated, but there was no air around it to dissipate that heat fast enough. Because it got to where? To the vacuum chamber itself. And a vacuum chamber, as you say, isn't a full vacuum. It's not close to an ultra vacuum, so there's still air in that vacuum chamber he had, and therefore there was dissipation. Now, if you had an ultra vacuum like so-called space and no walls around it close to it, there would be no dissipation of heat. Hey, Trinity Forzium. Hey, Trinity, how's it going?
Good. How are you, brother?
Good to see you, man.
Likewise. Likewise. There's a few people I know in your chat, so let me just say hello quickly to Adam Meekin and Tony Whitcomb, and who else did I see there?
I think everybody knows them.
Yeah, Tony Whitcomb still actually, he's the one that actually brought me to your channel.
Oh, is that right?
Yeah.
Well, it was good to see you in the chat the other day when I was doing the live stream in the street.
But
I didn't get to live stream on my channel last weekend because I was in a 7-day strike for medical information. And yeah, so I streamed with on another channel called Jason of the Disbury family. He and Harry MacDonald, who is John Smith Globeli, are some of the original Globeli tour guys from 2017, 2018.
Okay.
So we got together in Bath, England last Sunday and had a pretty epic time. I went the day before into another city called Wells. Had some pretty angry people, but I just wanted to say I think you deliver, aside from being exceptionally well scientifically versed, you deliver so calmly, and because I can see the guys trying to, they're struggling like eels in a bucket trying to get away from the evidence that you're presenting, and they
but you can't.
and they get and so for me, like I start getting annoyed with them being so obtuse. It's like, come on, man, look at this evidence. So
me too.
But I've learned to kind of just accept it through all the years, because after
really
you spoke, I mean, you've also realized that probably you get those people where you just it's a brick wall you're talking to.
Yeah.
So I've just realized if I get to that point and I see them, it's like, it doesn't really help. It's like talking to a zombie. So you would just let them do their rubbish and just let the arguments come.
It's a position of confidence that you're coming from. So it's a really strong position to hold, and it's good that you can hold that. I did make a comment earlier because I was sort of halfway bathing when I started listening to your discussion this evening, so I couldn't really comment in the chat. But one thing I did say earlier in the chat when you were talking about the surrounding medium, your guest sounds well educated, but he was struggling to kind of get his head around or wanting to accept the medium issue. And then, so what I wanted to remind you of, you probably know this already, but when we were young and getting science in school, living on the coast as I did in Durban, we were always told that, when you go up to Joburg, which is about almost a mile above sea level, you lose weight, So, and that's because there is less buoyancy, I think, in that.
Less medium around you,
yeah, there's less, so the air is thinner. And recently, like last year, when I traveled back from SA, I was overloaded on my suitcases quite heavily flying out of Cape Town. And so I paid very close attention to my bags. And then, thinking about all of these things, I checked them again when we got in at Joburg, because I had to weigh them again. And the bags were 200 grams lighter in Johannesburg than they had been in Cape Town, and they're exactly the same bag, untouched, just gone from one plane to the next, and it's the same scale system. that they use in these airports, but they were just fractionally lighter. And I've done the same thing where I've driven up to Joburg, jumped on a scale, and yeah, I'm lighter up here in Joburg than I am in Durban, kind of thing. So
but you see that's where the globers come in. They misrepresent that and say Eötvös effect. So they say it's due to Earth's rotation, and because you're further away from Earth's mass, so therefore you weigh less. But you see, that's just them having, again, that foundational belief that you require something to hold you down or you'd fly into space.
yeah,
So it all comes from a mindset on how you think about it. They don't think of the medium around it, which is a physical mechanism which you can prove. And they would choose something that's not proven as their basis for everything.
yeah. But and I mean, like the example I like to give people in the street is if I filled this space that we're in now with water, things would act differently all of a sudden. We would become buoyant or more buoyant because the medium had become more dense than
Exactly.
So it's quite simple stuff, but then they love to like complicate it with you need all of these equations and so on. But science should be observable and fairly easy to kind of go and replicate or test the hypothesis,
Exactly.
rather than sticking. And by the way, I was bought into this mainstream science for most of my adult life. I was trying to understand, how relativity could put everybody on the top of the ball, and that's how I see relativity. For me, that's how I know it's got so many different elements, but relativity is that everybody is standing on the ball and the top of the ball, and everybody is down below you. Which is why the curvature formula always goes down from you rather than it ever goes up.
It's always tangent to your feet. That's why I love telling the ballers, okay, let's look at the River Nile, for instance. To who is it flowing up, and to who's it flowing down?
Exactly.
I mean, if you're on top of a ball and another person on top of the ball, to him it's flowing down. To him it's also flowing down. But you see the contradiction here.
Same with the ship. When I say to people, if I'm sailing from England to France and the ship is leaving the harbor and it's going down, is it going to be going down when it leaves from France, or is it going to surely have to go up? And that's when people, no, but it's not up and down in the way that you think about up and down. I'm like, that sounds like it's level because it's neither up nor down.
Everybody on the earth is on the apex of the ball at the same time. Everybody personally has got their own specific little apex. It's crazy, isn't it? It's crazy.
But you see, they think down is simply to your feet. So they ignore that their globe still has a reference of up and down, north and south, based to the sun. That's why it's got a tilt of 23 degrees, because that's a reference. So you do have an up and down in your globe. But they ignore that and say, but no, down is just your feet. But that's just them simply ignoring their references. And I mean, the biggest thing that I think is the problem that they can't explain is based on general relativity. It's not the apple falling, but it's you rising up to the apple. So that requires the globe expanding constantly to be doing that. It doesn't.
And how does that work if like you drop an apple and the apple's rising up to you, but I haven't dropped anything, so how's that going to work? Or if I let go of a helium balloon at the same time. But I like to remind people on the street that the reason they use the apple is because nobody thinks about how the apple got picked up, how that 150 grams, 200 grams of water got to be inside of that skin. And the tree, of course, had to pump it or lift it or harvest it, and to create that, potential. Would you call it potential energy? Where once it breaks, then of course there's 200 grams of mass.
Yeah, they deny things like photosynthesis and stuff. They deny that the tree had to grow with energy, had put energy into the system of that apple, and as soon as it broke, this medium can't support it anymore. What happens is it has to transfer that energy, hence kinetic energy, and kaboom.
But lift a bucket lift a bucket of water to right underneath where that apple is connected to, to the tree, and it's going nowhere. It's just going to bob in the water. It's not going to fall because the medium is different. Same as the Johannesburg to Durban thing. At altitude, the medium is altered. It's thinner. That's why we don't breathe so well. Or the rugby players always had to go up, a week in advance to get used to the more rarefied conditions, atmosphere.
Yeah, exactly. Yeah, it's just medium dependent. That's what I was trying to explain to him with the cup. If you got the cup has a density to it. The medium around it can either support it or it can't. If it can't support it, the cup will fall. If it can support it, the cup will rise. It's as simple as that. And that's what their gravity is actually based upon. But because they have a belief, therefore they say it's.
Of course. It's they've taken the observation and created a model based on that observation, which is why it always, well, look, there's my evidence of the claim, but it's like, yeah, but that's the observation, and we would have seen that observation whether we called it, unicorn farts, as you said, and that's why planes don't fly over 65,000 feet really, because the medium there is too rare, too thin for them to hold that lift, so that's why they can't. That's why someone offered me the other day in Bath. It's like, okay, so I've got enough. I'm quite wealthy actually, and I've got enough money to buy you a ticket to go. This sounds like bullshit, of course, but I've got enough money to buy you a ticket to go on a Virgin Galactic flight. Would you take it? I said, absolutely, I would take it. But I know what I'm going to see is that I'm getting I'm getting a 5-minute vomit comet ride instead of the 45 seconds that Brian Cox got to have with the BBC or whatever when he pretended to be a spaceman.
If you understand how it works, they first train you on a simulator time and time. So they're conditioning you to know what to expect. So the time when you do actually go up, you're already conditioned to believe what you're seeing, but it's not what you're seeing. You even get planes today where their windows are not actually what you're seeing. It's simply screens. It's LED screens. And they can show what they want. And out there, you'll think there's space, but it's not. It's just screens. It's not actual looking out windows.
Yeah.
And the technology's been around for years.
Speaking of that, in the last few years, I've started to figure there's a reason why. You've probably done this flight yourself, but if you don't fly a direct flight from England to South Africa, you fly via Abu Dhabi or something like that, and oftentimes it's a daytime flight rather than the overnight flight that it always was, right, from Joburg to London.
Yeah.
And they're very strict about keeping the shutters closed. Now, to be fair, it's super bright. It's super bright during the daytime in the plane, and people are trying to sleep and so on. But I also think that it's part of their security protocol that we're not looking at what we're seeing, because when we fly at the daytime, we would probably see things that didn't quite add up.
Yeah, it doesn't add up. Exactly. No. They don't want you to look out, especially if you fly very constant, David. You cover the blind spots because like my brother, he went last week. He flew to Ireland. He also had to stop in Dubai before he went through, and he said also, the whole time you want to take videos for me, and they're like, no, close those shutters. You know what I mean? So it's the same thing.
They don't want to see everything that's down there. But, yeah, I've had some interesting flight experiences over the years. But if you're sitting, if anyone's still got a globe at home that they haven't crushed, you can take the globe and put a piece of string from Johannesburg to London, and then run that same piece of string over to South America, and you can reach all the way that length of string, which is an 11-hour flight in real time. That length of string will reach all the way over to the other side of South America, where there is currently a flight from Johannesburg. But the flight from Johannesburg is 4 hours, 15 minutes longer than the flight to London. And yet the string would tell you that it's probably a shorter flight, according to the globe.
Yeah, it's weird. But that's why even we love bringing up the argument that if you have Coriolis, if you're flying opposite direction, you're supposed to have a shorter flight because the ground would be moving underneath you. And we don't see this. So yeah, it's actually very simple. There's a lot of deception, I would say, based on even their modeling of programs. That's why I say even with the pilots, now they show this little 3D rendering of a globe. They say, see, we're following the globe, but they don't understand the data is based on the grid system. It's a flat grid system. They're just making the visualization as a globe. It doesn't make it a globe. It's the data that counts, not the globe, not the visualization at the end.
Yeah, no, it's very easy to take data, and I've spoken to people in the street who do like satellite work and some of these, work in some of these industries, and they have to concede that really what they're receiving is data. It's how you interpret that data. That's the key. And so just like a star could be 200 miles away or 100 miles away or something like that. It could also be, in their view, it's just, the math says it's billions of miles away.
Exactly. And it's all just based on a ratio system. I mean, all those things are based on Kepler's equation saying Venus and Earth are the same size. And that's how they have their ratio distances. And that's how they work out all the planetary scales. It's very simple stuff.
It's easily done to,
it's
work.
Just back engineering.
Reverse engineering, yeah.
Yeah, it's back engineering based on already creating a ratio system because of a belief.
I'm having a call I'm having a call tomorrow with an international airline pilot.
Okay.
Who lost his job because he wouldn't take needles. Australian.
Yeah.
And he's known since 2015, by the way, and there's nothing that he needs to convince him other than they don't make any allowance for curvature. And Coriolis is an interesting one because like there's so many weather systems that work counter to whatever Coriolis is. So I heard yesterday someone, not flat earth related, but they were talking about the American weather systems and how predominantly on the West Coast, over Oregon and places, Washington State, the weather is all coming from the sea in that direction.
Yeah.
And yet, if we were spinning like they say we were, then the weather should be coming from the east and not from the west. If I got that right.
That's interesting.
So yeah, most of their big weather systems come in over Montana, over that north western part of America. They come in that way, which is the opposite direction that would be if we were sort of moving and the air column was somewhat dragging. Which of course I love to remind people that because they say, yeah, but the atmospheric column, the atmosphere is moving with the globe, right? Now, and that's all again one of the magic tricks that gravity can do. And yet I say so it's moving 1,000 miles an hour here by my feet, and it's moving much faster 100 kilometers in the sky because that same column of air is staying with me.
Yeah. The rim velocity has to change with altitude.
Yeah. So how is that being motivated? But there's the jet stream and all that. That's like a one stream. That's not like the whole column of air is somehow supercharged to move at 2,000 miles an hour, whatever it would be at that additional radius.
But not just that. I mean, when last have you seen? I mean, gas is unboarded. It's moving in all directions. You take a ball and you just spin it. When last have you seen the air around it following it? It doesn't. It has got nothing to do with the surface. It's not going to follow it, no matter how hard you try.
No, but you see, they just need to invoke gravity, and then that's it. That's all they need, So it's a funny thing because they'll drop the mic, they'll drop the pencil, they'll drop the bag, and they'll go, "That's gravity." So I'm like, yeah, but call that gravity if you want to. But how do you explain how that's going to move a column of air without it being attached to? Yeah, but when you're in a plane and all that. Okay, so you're saying we're in an enclosed system then, yes? Because a plane is a closed system.
Yeah, it's the same arguments over and over. They love bringing those things up. They use false equivalences to try and correct their biases.
Yeah, that's not a test of gravity. Dropping something at best, that's an observation that once you drop something, it falls. That's it.
Mhm.
That's it.
Exactly.
And invariably, you had to lift it up. You had to take it out of its neutral buoyancy or its resting place or whatever. You have to move it. Try and force a soccer ball, football underneath the water. You see how much force that thing, or how it's trying to return to equilibrium.
Yeah.
Yeah. How are you going and saying that relative density has a vector to it?
Well, the problem is that on a globe there's no up and down, is there? So it kind of gets in the way of that, I think. But yeah, for me, obviously, there's up and down. Hot air rises, smoke, gases, light gases, they rise. Other things settle generally, and in this atmosphere anyway. And that's it. There's an up and a down, but they then kill that, just in the same way as they can throw gravity over everything that doesn't work or they can't prove. They just say that there's no up and there's no down. And I offer people this, that if we live on a sphere, and gravity has not got the force to constrain helium or the hot air or whatever, if that helium balloon was to be released in Ghana on the side of the globe, does that helium balloon start tracking towards the north, to the top? Because everything should go according to how it's coming out this way, at perpendicular to the globe, or from the side of the globe, and then staying at that perpendicular position without kind of naturally wanting to go to some top. If gravity's out of play. No, but gravity, they'll say, is still there. It's just somehow weaker, but eventually it grabs a hold of it and holds it in that line just above you at perpendicular to Ghana. It's like,
that's crazy.
Man.
That's crazy. That's what I said. They love ignoring rim velocity. As soon as they take rim velocity into account and tangential velocity, then they're going to see it doesn't make sense. But they have to run away from that. That's why they always just, conservation of angular momentum. But they don't actually understand what they're saying when they say that. That's the big issue.
So very clever. Yeah, sorry to interrupt.
I just have to say, Adam Meakin's very clever with this. He says, synchronicity, that's the air, at increasing its violation of the first law of thermodynamics, even if you permit the ball whipping air. Exactly. Because it's not transferring anything then. It's just keeping the energy.
Well, Adam Meakin, my son is playing with Adam Meakin's Lego set. So we know Adam very well. And we've done some Globe truth tours together. Adam got arrested in Rome on the Globe Light tour. That was a funny day out in 2019.
I remember that.
Yeah.
I remember seeing him getting into the car. It was like, what's going on? Why is he getting arrested? It's like, all the Globes are saying, no.
And let me tell you, I'm standing over him going, I want to rugby tackle this policeman. But I know that if I touch the policeman, I'm in big shit myself,
Yeah.
So that was a funny day. That was a funny day on tour. But Adam Meakin is a real trooper, and he's definitely one of those guys who's looking for, he's got a super smart head on him, and he's looking for what is provable and what we can demonstrate. So I do enjoy having Adam in the room.
If there's one superpower I'd like to get from Adam, and that's maths.
Sorry, I didn't hear that. My audio is really low.
If there's one superpower I'd love to get from Adam, that would be maths. He's very good at maths. There's like a
well, I won't belabor this, but Adam and I don't agree on something to do with maths, and that is, and I'll just throw this into your pot. You may go the same way as the smarter guys than me go, but I went on Jeranism a few years ago with Bob, rest in peace, Bob, from Globebusters. Yeah. I'm sure people know.
Yeah, we know. Yeah, nice.
Bob Nodell passed, but and he will never be forgotten. But he invited me on to Jeranism to talk about 8 inches per mile squared, because whilst I agree that the maths works fine, it turns out that every circle, because that's what we're measuring when we do that, every circle is going to have the same ratio of drop. It may, depending on the radius, will be a different amount. The bigger, if it's a basketball or a golf ball or a globe, it's going to be a bigger amount, of course, the distance. But I say this, that the 8 inches per mile squared is like a disinformation that I've pushed and we've been given to try and dilute what we say about it, how insane it is to live on a globe, and that there's 8 inches per mile squared isn't there. But see, I put it like this, that if I was a ship's captain and you called me at every mile and said how much curvature is in the next mile, I would say it's 8 inches, and you would say that's correct. Because from the observer point of view, the 8 inches calculator starts from 0.
Yeah.
However, if the ship is 5 miles away from the port and I'm watching the ship, I would have to say to him, no, it's 8 inches times 5 squared, right? And so that would be obviously 400 or whatever. That would be a much bigger number, that the next mile is going to have X amount, 400, 800, whatever inches of curvature, because it's kind of growing that way. But when you look at a ball, doesn't matter what the size of the ball is, the curvature on the ball is equal no matter where you land on the ball. Mm-hmm. It shouldn't matter at all. So what I say is that the 8 inches per mile squared is relativity repackaged for the flat earth debate. Because what it does is it puts you on a 0 point, which there would never be a 0 or a flat point on a sphere. It's always going to have curvature. The step before that you're measuring your perpendicular or your 0 from would have an amount of curvature. Okay. Not only that, when we draw pencil lines on a 2D piece of paper, so we're inscribing a column rather than a sphere. But anyway, when we do that, every time we draw a pencil line, we draw that pencil line horizontally. So that pencil line doesn't need to take any account of the angular change of the ship, having gone from, this is my 0 now, I've changed, I'm in South Africa, I'm now 90 degrees pointing down. And I don't think we actually, with 8 inches per mile squared, I don't think that we actually have to account for that. We're only just saying the drop from the original
because the
horizontal line.
Yeah, the 8 inches per mile squared is just simply a ratio, like Adam's saying. It makes a parabola, as I say, because it's only accurate to 1,000 miles. But that's one thing I say. It doesn't matter actually, because you never do observations to 1,000 miles. It's impossible to do those observations.
Yeah.
So it has to still conform to their globe. And because they live on a blade spheroid, you can't really use the 8 inches per mile squared because it has a different ratio value when you get to the equator, quote unquote. But that's why I don't bother about that argument at all, because it's actually just
But imagine this, which is cool. But imagine this, because like let's say you're traveling from England to France and it's 30 miles across the English Channel. The first mile is 8 inches and the last mile has got 150 inches. I don't know, I'm just guessing, right? But the last mile has got 150. But when you turn back and go back to England, you would say the first mile has got 8 inches. So in practical terms, that doesn't make sense.
Yeah.
What I say to people is that actually when you take any sphere, any ball, choose any ball you like and measure it, and you've got a journey of, in the case of the globe, it's 12,500 miles from North to South Pole, and you're going to drop down 8,000 miles. So it's a ratio of 12 and 8, which is actually works out to be like 1 kilometer should have 600 meters of drop or rise, because obviously, relativity is fake. If you live on a globe, the truth is that you have to be on some of you have to be on the side of the globe, some have to be underneath the globe, and so you would actually be looking uphill, essentially, to be going, up the hill. So for me, I know obviously I can't convince people to say this, but imagine if right at the beginning we'd say, well, it's that's the journey, and every part of the sphere. I know oblate spheroid gets thrown at me as like the kind of, well, it's not exactly a sphere and so on. And then I'll point to to the pictures of NASA's. It's perfect blue marble, but imagine if we'd always been saying, by the way, if you lived on a globe, you would have 600 meters of curvature for every kilometer that you moved around you. It would be either up or down, but you're going to have that. It's like being on the side of a mountain, even though it's as big as it is.
And that's the
but
point,
anyway, I just thought I would share that just as an anecdote, because I love Adam Meakin, and we've done a lot of good stuff together. But yeah, that's one thing that I still have a kind of obviously the globe is a fake construct. But when I tell people that it's 8 inches and 50 inches a few miles down the track, they're like, yeah, well, maybe it's there, maybe it's not. And as you say, rightly, we can't see 1,000 miles. We can't really see 100 miles, except for a few rare occurrences. So even carry on.
So I would say the 8 inch per mile square argument is perfect for people that are not in this topic. I mean, like the people you get on the street are perfect because they're still fresh to it. They haven't been really come to the argument yet. So if you give it big, it gives a visual argumentation to them. Say, yeah, I'm supposed to actually be seeing this drop. Do we see it? No. So I would say it depends on the audience you're trying to achieve to talk to. But if it comes to like people that's been in this argument a few years, I think 8 inches per mile is then sort of mute. But when it comes to fresh minds, like you get on the everyday streets, 100%, because it puts a visual implementation to see, oh yeah, there is something horribly wrong here.
That's what convinced me actually right at the beginning was 8 inches per mile squared, because I grew up in Durban, and I saw things. I'm flung rocks from Durban and things like that. Like, no, I shouldn't be able to see that according to your formula.
I mean, I was a few years back in Cape Town, and we went Strand, and I was lying down on my stomach with my iPhone, and I could see the shore of Robben Island. I mean, it's 11 k's away. My iPhone's camera is like literally this high off the ground. How the hell are you supposed to see that?
Yeah, but it's a mirage.
It's always a mirage, no matter what.
Yeah, absolutely.
But it's awesome having you on. I really appreciate you coming on because
Awesome. Well, I really I wanted just to give you a little bit of props for being awesome at what you do. And I was, like I said the other day, I didn't see you reply in the chat, but I'd love to have you on my channel for a little chat, my new channel. And we can chew the fat sometime. So thanks for giving me a little bit of airtime.
Awesome.
I'll leave you guys to it.
And yeah, guys, please do go look for Trinity's Force channel. Definitely well worth it to go and subscribe. He has awesome chats with people. But that's what I love about it. The raw chats with the people that's only getting it, and you can see their cogs turning in their heads because it's like they've never thought of it like that before. And it's like,
it makes a big difference, and I do it partly to try and inspire other people to go out in the street and and try and break the algorithms, because how much constraint we have in the social media sphere.
Definitely.
It does. Some people have never heard of it, and nowadays a lot more people have heard of it. Some come with their pre-packaged Professor Dave rebuttals, and others are like, you know what? In fact, I saw a lady in Wales the other day. I think it was on video. She came up to me and said, I saw you in Glastonbury the other day with your banners, and I only drove past, and I went and researched it, and I'm in. It didn't take me long.
Brilliant.
So, and I think probably people know this, but the last 3 years since the COVID pandemic, that has really helped to shake a few people out of the trees and go, gravity's a hoax. Anyway, definitely. I'll leave it there.
Oh yeah, definitely.
We'll speak again.
Yeah, thanks, mate. Really appreciate you coming in.
Bless, man.
Very nice guy.
Yeah, he sounds cool.
Oh, sure. Rob Keane says, what drop? Adam Eakin says brilliantly. In reality, there is none. That's true. But yeah, guys, Trinity 4, he does street activism. And like I said, it's very nice because he talks to fresh minds with people that don't really have come to the argument, before. So they don't have how can I put it, the set walls that the anti-flat earthers and stuff have.
Yeah.
So
like
they fresh into it. If you explain it the way he explains it in a rudimentary fashion, you can see their cogs turn. They're like, yeah, this just doesn't make sense because what the globe presents and what the argument is two different things.
Yeah.
So I think we're going to probably end the show, because I mean,
decent.
Almost 3 hours long, guys.
Yeah. Well, yeah. Just in that.
2 hours and 46 minutes now.
Yeah.
So I just want to say thank you everybody for coming. You guys rock. Thank you PJ also for coming on the stream.
No problem.
It was good having everybody here. Thank you for coming. Thank you for the super chats, for sharing and caring. I mean, there was quite a few people on the chat, so I'm really happy about that. I'll see you guys again tonight because it is again the next day. So I'll see you guys all tonight or tomorrow, wherever you are in the day. Thank you for coming. That's all I can say. Many blessings. May you have an awesome night or day further. May the pressure be with you. Cheers.
Good night.